Hello, everyone. Welcome back to Zig. All right, today we're going to continue the journey of learning Zig. Just as a quick recap, last time we did like 7 or 8 exercises from, what were they called, those exercises? They had a Ziglings? Temp/Zig. Ziglings. Yes, Ziglings. There we go. And exercises. Yes, so we did 8 of them. So we will continue with those. But the other thing that we also did was we found a book, which I need to find again. And I reinstalled the browser and lost all the tabs. So we had the initial introduction somewhere. Get started. There we go. And there was learn section, in which at the end we had the things, and there was project-based book. There we go. That's the book. Get another link. And yeah, so we basically finished around here. Does it have like a dark mode? No, it doesn't. So sorry about that. Finished with how to learn Zig. And now we'll be actually starting with creating new objects. All right. So let's continue with the book first a little bit more, because it's going definitely slower than what the Ziglings tutorial goes, because they just go little by little, give you little chunks. But this gives us a lot more context, and I think this is a little bit more valuable right now than just doing exercises without having like decent explanations. So yeah, let's just read more. I'm gonna zoom in a bit more. Okay, those columns don't disappear that much. Alrighty, so creating new objects in Zig. An example, identifiers. So let's talk more about objects in Zig. Readers that have past experience with other programming languages might know this concept through a different name, such as variable or identifier. In this book, I choose to use the term object to refer to this concept. So that's a very interesting choice, because object usually means the thing that's allocated on a heap. So that's, I must say that is a bold choice. I guess just for the sake of confusing people. So to create a new object or a new identifier, I like the word identifier. In Zig, we use the keywords const or var. I mean, identifier, it doesn't even... don't like this terminology, because an object, it is used to refer to something that's usually allocated in a heap and some kind of generic object, something dynamic, right? Identifier is usually in languages refers to any kind of name of a function, name of a class, name of a variable. That will be an identifier, something that the compiler or parser or whatever recognizes that, okay, I should hold a pointer for that. It's just like a name label that then gets removed. And variable, that again isn't like the best choice, although closest to what people understand, I guess, as in something that holds the value, but depending on language, it might say, hey, this thing actually changes over time. So yeah, it is a hard choice. So let's just be aware that whatever he calls object is whatever, a variable. So to create a new object in Zig, we use the keywords const or var. So we have just 2 keywords for that. Okay. These keywords specify if the object that you are creating is mutable or not. If you use const, then the object you are creating is a constant or immutable object, which means that once you declare this object, you can no longer change the value stored inside this object. Okay. All right. how deep does it go? If I'll make a constant list, does it mean that I can't expand it anymore, or I can't just change what it references? I think that would be a big part of how that works. I really wonder how they solve that issue, because there's just so many ways you could make something constant or refer to something. On the other side, if you use var, then you are creating a variable or mutable object. You can change the value of this object as many times you want using the keyword var, and Zig is similar to using keywords let, mute, and Rust. Okay. Yeah, I guess let is just create some kind of value, and we mark it as, create a variable, whatever, mark it mutable as in it can change over time. All right. Makes sense. Very simple concept. So constant objects versus variable objects. In the code example below, we are creating a new constant object called age. There we go. Const age is 24. This object stores a number representing the age of someone. However, this code example does not compile successfully. Oh, this one here, because we want to change, right? Because of the next line of code, we are trying to change the value of the object age to 25. The Zig compiler detects that we are trying to change the value of an object or identifier that is constant. And because of that, the compiler will raise a compilation error, warning us about the mistake. And hello CPN, how are you doing? You can't see the screen. Oh, because I haven't switched it. Sorry about that. Thank you for pointing that out. Oh no. A rookie string mistake. All right, so the Zig compiler detects that we are trying to change the value of an object that is constant, and because of that, the compiler will raise a compilation error warning about the mistake. Okay, great. That makes sense. And we even have an example of the error. So we have file name, which line, which column, error cannot assign to constant. Okay, so that's a nice clear error. I think something like that in nim is like really cryptic. So if you want to change the value of your object, you need to transform your immutable or constant object into a mutable variable object. You can do that by using the var keyword. This keyword stands for variable, and when you apply this keyword to some object, you are telling the Zig compiler that the value associated with this object might change at some point. Okay, simple. Thus, if we come back to the previous example and change the declaration of the age object to use var keyword, then the program gets compiled successfully. Because now the Zig compiler detects that we are changing the value of an object that allows this behavior because it's a variable object. However, if you take a look at the example below, you will notice that we have not only declared the age object with the var keyword, but we also have explicitly annotated the data type of the age object with the U8 type this time. All right, there we go. We have variable, age, and we have the TypeScript style or Rust style or Go style, I believe, as well, of specifying a type. There we go. Unsigned integer, 8-bit integer. There we go. So here, the basic idea is when we use a variable or mutable object, Zig compiler asks for us to be more explicit with what we want, to be more clear about what our code does. This translates into being more explicit about the data types that we want to use in our objects. SPN says, I read somewhere that making the error messages user-friendly will be a priority after version 1.0, which could be years from now. Yeah, but so far they weren't bad. I just have bad experience with error messages when it comes to nim. They're like really confusing. I mean, you need to really focus to understand what they're even trying to say. It's crazy. Therefore, if you transform your object into variable or mutable object, just remember to always annotate the type of the object explicitly in your code. Otherwise, the Zig compiler might raise a compilation error asking you to transform your object back into a const object, or to give your object an explicit type. Alrighty. I mean, so it doesn't assume that it's an integer 32? It just really wants that? I actually want to test that. Let's say we're gonna go here and we're gonna create like a whatever new file. We're gonna call it 00test.zig. And we have this code, right? It already has a problem in it. I guess because we don't have a main, right? How is it? Public function main. Let's even import standard. Why not? There we go. There we go. And there we go. Now it's happy. And here we were doing Zig run. We're in exercises, so we'll be 000 test Zig. Okay, that run. Great. So what happens if I'm going to remove the U8? Comp time int. So if we don't have anything, it will just use comp time integer, and because it's a variable, it will just say, oh, sorry. There we go. Variable of time comp time must be const or comp time. Very interesting that it doesn't assume that it's an integer, like, int 32. That's actually awesome. But I can do int 64, I guess, and it's happy, right? Can I do like 128? I can. Oh, can I do 512? Doesn't complain yet. Okay. All right. I like that. Can I do something like u512 unsigned integer and make this minus 25? Save. Will it tell me that I overlapped or not? Okay. Cannot represent integer value -1. Okay. So, I really want to do something of this sort. I really want to wrap it to the maximum number, because right now I don't know how to get the maximum number. Integer overflow. Okay, so we've got a warning about it's just straight up panic, and I can't force it, unfortunately. Too bad. Too bad. I'm sure there's a way of like different operator to actually force it. But yeah, okay, this is fun. I really like that. Can I do like that and break my computer? It still complains about overflow. Other than that, oh, because I'm not using it really, so it probably doesn't care. Print age. Oh, that wasn't print. That I'm thinking of Dart. Okay. And CPN says the default type of an int is comptime int, standard math max int. So be standard math max int. And we need to provide the type, which will be, I guess, u5120. Or do I need to throw in the word comptime above it? Okay, so I'm getting that, and I need to do now, in some way, standard, and what was it? Dot. It wasn't just std out. It was like debug print, I think. Wasn't it? Hello. And there we go. Copy. Paste. Okay, so it is the same thing. And we just put the bracket somewhere in there. So it'll be the value is, and I think I'm going to because we want to put in the age. But what I would do, just in case, let's start with 16, okay? Because it might be a little bit too much. I don't know if this is gonna work with that, but let's see. Okay, so that printed out correct. All right, so we're gonna go 64. We're gonna have a large number. I mean, how did that work? We tried to assign a really, oh wait, not the other way around, sorry. We tried to assign small number to large spot. Okay, so what happens if I'm gonna, because, oh gosh, that would be so large. Mind-bogglingly large. I really need to see that happen. That is a large number. So we're just gonna throw in a 0 at the end. And hope that, oh yeah, it can be a third, sure. Let's hope that this isn't gonna hang the thing. Okay, all right. So this is the how large number we can represent. I really like that. We don't need a special library to handle really large integers. This is fun. Okay. I can imagine just making like a simple calculator, but instead of that, just saying, you know what, I'm gonna use integer 64,000, right? And doing all the calculations in that system just to screw with it. Oh dear. Oh dear. Yeah, that is a large number. CPN says, also, this is new to me. I didn't know Zig can do this. I saw many times that Zig can do something like U7, like 7-bit value, right? I mean, it can be extremely useful because I think Zig has structs that you can actually compact. How I could describe it. So basically, there's like whole talks and probably half of books on this subject. But if you create some kind of structure, if I don't even know how to make proper comments, this doesn't seem to work. But if you have some kind of structure, let's so you have a struct ABC, right? You can define something like, let's say you're making a game, right? You're gonna have 20,000 objects of this thing, right? Okay, no multi-line comments. We'll deal with that. So we have a struct ABC, and this is not gonna be Zig formatting. I don't know Zig formatting for structs yet. So let's say that you're making a game, and maybe your character has health, right? We have health. Maybe we have some kind of several flags of, you know, is flying or can shoot, is reloading. Few of those, and maybe at the end we're gonna throw in that we have maybe lives left, and lastly something like, oh no, this is enough, I think, right? Okay. And CPN says data-oriented design. I watched a bunch of talks about that. Possibly data-oriented design, not even saying about design. Just the fact that, let's say you have a game where you need to keep track of 20,000 characters like that, right? 20,000 objects. So you want to store them in an array, okay? Often you would have even probably in some situations more than 20,000. So you think of it, okay, health in standard units, like the way you would do it normally, you would say, okay, this is gonna be U8 because this is usually the smallest you can do. So it's value from 0 to 55, right? Let's just do double slashes so it looks like a comment, right? Then is flying, it's gonna be a boolean. So we have 0 to 1. Can should will be another boolean. And is reloading is gonna be another boolean. And at the end you have lives left. Again, you go with U8 because it's the smallest value. All right. Maybe let's also throw in a score, which will be you want to do U16 or something because you want to go up to 2000. So suddenly you have something like that. The way the computer, if you're gonna create the struct, what a computer or your compiler will do, like in a very naive situation, because some compilers actually try to optimize it, is that the computer will do stuff in blocks of, for example, I think even not U8, it'll be blocks of some larger blocks, maybe like int32 or something. It's a number of bytes. But right now, you have, let's say it's in 8 bytes, right? So you have this thing, which will be like, okay, we assign those 8 bytes here. So this is 8 bytes. This is gonna use 8 bytes as well. Even though it can hold only 0 or 1, really as a separate variable, it will be entire byte. So you're not saving the data unless your compiler optimizes it and combines them too in some way. But you need to go into effort to actually make it work. And this will be also 8 bytes, lives left, 8 bytes, and this will be 16 bytes. So, it's not a lot, but you have 1, 2, 3, 4, 5, 6, 7 times 8. So, I mean, why am I calculating that? 56. So that's gonna be 56 bytes, okay? Times 20,000. 20,000 times 56 divided by 1024. So that will be, okay. So that's already more than 1 megabyte of data, right? And this is like a really minimalistic thing. If you have other objects or whatnot, this is gonna be way more. And remember, in some larger games, really, your scene or whatever is being held in memory, it's literally hundreds of thousands of objects, depending on the game, of course. Especially if you need to hold triangles or some other things, you have a lot of data. So what I learned is that Zig actually has very smart system of packing those structs into more optimized ways. So I could really, health is gonna from 0 to 100, right? So really, if I'm gonna do U7, I'm gonna have a value from 0 to 127. Like Vampire Survivors, exactly. Each little particle that something's going on, it needs to not track its velocity, so that's already 3 numbers. A rotation, probably some lifetime when to go away. So many things. Each thing needs to hold so much state. So in here, I could do U7 because that will give us a value up to 127. All right. So our health up to 100 will fit in this. Is flying will be again a boolean. Can should will be boolean, and reloading will be a boolean, and lives left. Maybe you just want literally to have, up to 3 lives left, right? Because you don't need that and more. U2 would be 0, 1. So you have 2 states. If we're gonna use U3, that will be a little bit more. That will be 4 different states. So you can really have 0 lives, 1, 2, or 3. So this is actually perfect. 3 lives. And then we have score, which could be, I don't know, U10 or something, because you have some requirements, right? By the way, bool in Zig uses only 1 bit. Oh yeah, because this is bits, right? Sorry. So yeah, so we could do U2. There. Thank you. And there we go. We could do something of this sort. And what Zig is going to do, because it knows how the underlying architecture works, how it structures. In our case, we pretended that we have 8-bit system or something. Therefore, it's gonna pack those two together into a single value. So really, those two together will be just 8 bytes. So it will end up being 7 and 1. Then it's gonna do 1, 2, 3, 4. So this is 4, and probably won't be able to combine them. So this will be probably, those 3 will end up being 4. So these will end up being 4 bytes, which will be 1 8-byte. Okay, because the system can't do more. So we're gonna do this. And this is gonna end up being 16 bytes anyway, because we couldn't do much about that. But that brings us to, okay, we remove from 56 to 24 bytes. And suddenly we decrease that to probably something around 400 kilobytes. Something like that, right? And magic. Yeah, but I think in a real system, these would be, I don't know what the terminology is, padded or something, where each boolean would really take up like 32 bytes of data, or maybe on a 64-bit system, it will be literally 64 bytes. I don't know. I'm not sure. That will be something to check. But I know that this is a real thing, and it can really sting you if you're doing something where you really need to start conserving memory. But Zig abstracts it away in a nice way. Okay. So, yeah, with U7, it will be 127. There we go. Beautiful. Okay, we learned something. I had no idea that you can go up into larger numbers, but that's absolutely great. It's probably very unoptimized because suddenly, your processor has tons of like specialized hardware just to calculate like separately maybe 32-bit numbers, separately 64-bit numbers, and everything else maybe just converts in the meantime, right? So if we're going to throw a 512-bit number at it, it probably won't do good. Maybe it has something to do 128 or 256 for some encryption stuff, but I wouldn't expect much beyond that, so it would be like way, way, way slower, but hey, you can calculate that if you want. SPN says, so much for no hidden control flow. Well, it's not really control flow. At that point, it's data design, and you can't really flesh that out more. Zig does what you would want it to do. I'm sure there are some specific mechanisms for that. Maybe we'll learn about it. All right, so we learned about that. We learned that we have this comp time int if we don't specify the type of an integer variable. So this is very useful. I like that. It forces us to be explicit in some cases that could be a source of error, because like, oh, I assumed it would be int 64 or int 32 or something. Or depending on the platform, sometimes, what was it? Some languages have it where you just do int without any number behind it. Like, oh, this is an integer. On a 64-bit machine, it will be a 64-bit integer. On a 32-bit machine, it will be a 32-bit int. And suddenly, your code behaves differently on every different platform. And what if you're dealing with 16-bit microcontroller or 8-bit one? Everything falls apart. Here it doesn't, makes me happy. All right, declaring without an initial value. By default, when you declare a new object in Zig, you must give it an initial value. In other words, this means that we have to declare and at the same time initialize every object we create in our source code. On the other hand, you can, in fact, declare a new object in your source code and not give it an explicit value. But we need to use a special keyword for that, which is the undefined keyword. Oh, so before we read more, so I would expect that the undefined keyword, it doesn't assign, it probably just doesn't assign anything. It doesn't reset memory when the thing is initialized, but it probably is just a hint for the compiler that later on you must set it before you read it, and something of that sort. That's what I would expect. It's important to emphasize that you should avoid using undefined as much as possible, because often you use this keyword. Because when you use this keyword, you leave your object uninitialized, and as a consequence, if for some reason your code uses the object while it's uninitialized, then you will definitely have undefined behavior and major bugs in your program. Oh, so it actually, the compiler won't force you. It just leaves the data that the variable is, because as far as I understand, when you create a variable, right, and you don't give an initial value, it just reclaims a chunk of memory and the data is still there. Some random data of whatever was in there. It just there, right? So you're gonna get some random value for no reason. So I want to try that right now without any further ado. Let's say that I want U128, okay? Some large number. And let's just see what that 128 is. And we're gonna print it and it's all gonna be fine, right? Sure. Oops. And CPN says this is a valid syntax. Var age is at as U8 and 24. Okay, I guess you can do that. This will force it inferred, right? That is true. In release mode. Okay. Oh, in release mode, not in debug mode. So this is fine, right? We can represent a large number, 128 bits. So if I would just say that this is U128 and say it's 0, it's gonna be 0, right? There we go. But what if I'm gonna say undefined? Can I run it? Yes, I can. And notice that we have some random number. I'll run it again. We have the same number every time for some reason. But we have an undefined number, right? What if I'm gonna say var not age is whatever U8 and it's gonna be 1, 2, 3, okay? And then we're gonna say not age is 1, just to have that thing. I wonder if suddenly this being an offset or something is gonna change this value. We're gonna recompile. No, it didn't change the value. Interesting. Why is it always the same value? Spian says in debug mode, undefined initiate the value of 101010. Oh, so it's always the same thing. Okay. Let's do Zig run help. So that's lots of help. That is a lot of help. Zig run help grep release. No. How do I go into release mode? Object with assembly. Incremental. Compile options. Profile. This language dependencies. Create a module. Error. CLang and all that stuff. Target OS mode. Default is debug. Release fast. Okay, so let's do release fast. Release fast. Will that work? Okay. The value is 0. Okay. So we've got 0. It just zeroed it. Every time it's 0. Okay. Interesting. I wonder if it's because when the program is initialized, the system gives it a chunk of memory and it just randomly zeroes it for safety reasons or something. Don't know. It might be because we have very, very, very small program. That's that's constant no. Var. I don't know. Yeah, it's not guaranteed to be 0. Exactly. I just hope to find something where it actually is 0. I mean, it isn't 0, but okay. I guess just, it's not guaranteed. Don't try it. It's on you when you use the undefined, right? So in the example below, I'm declaring age object again, but this time I do not give it an initial value. The variable is only initialized at the second line of code, where I store the number 25, in this object. Okay? Having these points in mind, just remember that you should avoid as much as possible to use undefined in your code. Always declare and initialize your object, because this gives you much more safety in your program. But in case you really need to declare an object without initializing it, the undefined keyword is the way to do it in Zig. Okay, so I guess this will be very useful for situations where you just, the situation I can see it useful initially is that initializing it with a value, like setting it, is yet another thing to do. Therefore, it will hit performance for some reason. That's the only thing I can think of. Like why one would even attempt that. Let's say you need to create a list of items or like an array. You make it undefined so that you don't bother zeroing it. And therefore, because you will fill it or something in the future, and therefore it's guaranteed that you're going to override it and not read the invalid state. So at that point, I can see it being useful. Okay, I'm already seeing that I want to go back into the CBOR and implement it in Zig and see how that will feel, because that could be an interesting challenge. I know that I already looked a little bit into Zig and game development, and I would like to kind of make one game that I always wanted and try to do it in Zig. Would be very interesting. But I don't know if it will be too much work in Zig to go something that low level. I don't know. We'll see how it goes. First, I need to learn the language. So having these points in mind, just remember that you should avoid as much as possible. Yeah, okay. So 143. There is no such thing as unused objects. It's useful for initializing structs or arrays. Yes. Yep, exactly. All right. So every object, being constant or variable, that you declare in Zig must be used in some way. Or its compiler would just compile it away, I guess. You can give this object to a function call as a function argument, or you can use it in another expression to calculate the value of another object, or you can call a method that belongs to this particular object. It doesn't matter in which way you use it. Excuse me. As long as you use it. If you try to break this rule, for example, if you try to declare an object but not use it, the Zig compiler will not compile your Zig source code, and it will issue an error message warning that you have unused objects in your code. What if I need to put in some variables in there so that they take up memory so that I can do some weird memory trick to make things aligned? I don't know. I'm trying hard to make an edge case. Let's demonstrate this with an example. In the source code below, we declare a constant object called age. If you try to compile a simple Zig program with this line of code below, the compiler will return an error as demonstrated below. Constant age 15. Sorry, unused local constant. So it complains also about constants, not just variables. That's interesting. Every time you declare a new object in Zig, you have two choices. You either use the value of this object, or you explicitly discard the value of this object. Explicitly discard. Interesting. To explicitly discard the value of an object, excuse me, constant variable, all you need to do is to assign this object to a special character in Zig, which is the underscore. When you assign an object to an underscore, like in the example below, the Zig compiler will automatically discard the value of this particular object. Okay, so they're speaking, whatever, talking about returned values also. I guess we can have situations where a function returns a value and we're obligated to use it in some way so that the compiler makes sure that we don't forget about things, I guess. And I can imagine it being that, oh, we're being returned something and then we need to free the memory for it later. Therefore, we need to ensure that we are storing that object somewhere, right? So for those situations where, oh, just some random integer was returned, we don't care about it. We just use an underscore, right? So you can see an example below that this time the compiler did not complain about any unused constant and successfully compiled our source code. Okay, so we created the constant and we used it as in just voided it, whatever. This literally does nothing, I guess. Assigns it into nowhere. Now remember, every time you assign a particular object to the underscore, this object is essentially destroyed. It's discarded by the compiler. This means that you can no longer use this object further in the code. It doesn't exist anymore. Okay, so if you try to use the constant age in the example below, after we discarded it, you will get a loud error message from the compiler talking about a pointless discard, warning you about this mistake. Right, we try to do something. We try to, okay, so age becomes discarded. That's interesting. Like we modify the constant. Pointless discard of local constant. Huh. Hey Taras, what's up? Have you ever heard about discarding a constant value so that it cannot be used further in your code? That's a new object, new concept probably, right? What the heck? This same rule applies to variable objects. Every variable object must also be used in some way. And if you assign a variable object to the underscore, this object also gets discarded, and you can no longer use this object. This is kind of cool. Just to make sure that, you know, if you don't make any accident and reference that in the future, huh? That says bye-bye speedrun. Yep. Alrighty. You must mutate every variable object. Oh, that's interesting too. So if it's a var, you just, okay, so it's basically this is kind of equivalent of warning. So in many languages, even in C# or something, usually your IDE or whatever says stream watch speedrun. Yep. Well, it can't speed me up. That's for sure. Yeah, here it's an error, but I'm saying like in many languages, when you use some kind of IDE and you, let's say, define a variable and then maybe never modify it, as in never really assign it a value or something, you used it only to read it. Even in JavaScript, your linter or something will just tell you, hey, mostly as a warning, like, hey, you have a variable here, but you could make it a constant because you never use it, right? But give you that hint. You can configure it to be an error, sure. But here is, I guess, by default, and something tells me can't switch it off. Oh no, maybe you can. But basically, you must mutate every variable object. That's a nice rule. Every variable object that you create in your source code must be mutated at some point. In other words, if you declare object as a variable object with the keyword var, and you do not change that value, if you do not change the value of this object at some point in the future, the Zig compiler will detest this and will raise an error warning you about this mistake. Okay? The concept behind this is that every object you create in Zig should be preferably a constant object, unless you really need an object whose value will change during the execution of your program. Okay, so yeah, encourage. Okay, this gives me vibes of that Dart project that has Nazi compiler, that Nazi linter that just shouts at you at every unnecessary thing. CPN says, yeah, Taras, you still there? And 90 Director says, we've got from 0 to 0 speedrun before GTA 6. Okay, so what? GTA 6? Alrighty. I guess I don't get a reference with the 0 for GTA. Sorry about that. Okay. So if you try to declare a variable object, such as where I live below, and I do not change the value of this object in some way, does it compile raise an error message with the phrase variable is never mutated, right? Bam, I just discard it. It will be like, you know what? You didn't change it, so consider discarding a const instead. Okay. I mean, that's good thing to know that, okay, I need to be aware of this or I'm just gonna be making a bunch of errors. And Travis says, hello, Zig is a nice lang. I've been using it several years now as a hobby lang. Gotta run, but hope you'll be on when I get back. I'll be here probably, what time is it? 2.5 hours. So, see you. It's nice you stopped by. Primitive data types. Okay, we're finally getting to something, right? Zig has many different primitive data types available for you to use. You can see the full list of available data types at the official language reference page, okay? I want a sneak peek. Okay, we've got all integers, tons of stuff for C. Oh, and that's it. Really? Okay, that's not a lot. Just lots of numbers and that's it. Huh. Okay, great. Well, here's a quick list. Unsigned integers, as in U8, 16, 32, 64, and 128. Signed integers. Okay, the same thing, just I instead of U. And float number. And CPN says, by the way, there's dark mode. The switch is near the title on the left. Oh, on the left. Okay. And Travis says, sounds good. Catch you soon later. Oh, this little tiny thing is a switch for dark mode. Oh, wow. That's the weirdest switch ever. Okay. Thank you. Thank you, CPN. I would have never noticed this thing even there. Okay, so we have our unsigned integers and whatnot, signed integers, we have floating numbers, we have, okay, we've got F16, that's fun, 32, 64, all the way to 128. Okay, this 128 makes me very happy. And then we have booleans with just a bool, okay. Everything's lowercase so far, so I'm very happy. And we have CABI compatible types, so we have, okay, we have long, character, short, U short, int, uint, and all the other arcane things, right? And then we have the pointer size integers, which is I size and U size. Okay, they're pointer size, so this will be probably system dependent, right? Either 32 or 64-bit. All right, cool. So going into arrays, all right? Wow, we actually jumped from using U8 only in a few examples. Quick rush through all the possible types, and then, wow, okay, let's skip all this stuff and go into arrays. Why not? Uh, I like it. You create arrays in Zig by using a syntax that resembles the C syntax. First, you specify the size of the array. For example, the number of elements that will be stored in the array. You want to create inside a pair of brackets. Okay. Then you specify the data type of the elements that will be stored inside this array. All elements present in an array in Zig must have the same data type. Okay, so they are, what is it, homogeneous? For example, you cannot mix elements of type F32 with elements of type I32 in the same way. After that, you simply list the values that you want to store in an array inside a pair of curly braces. In the example below, I'm creating two constant objects that contain different arrays. The first object contains an array of 4 integer values, while the second object an array of 3 floating point values. Okay, so a constant ns, 4 u8s inside, 1, 2, 3, 4. There we go. This one will be ls, any number of f64. In this case, from Zig Links, we learned that this will just calculate this number for you, right? And that's it. So I like that this is optional, but if you want, you can specify it. Because there might be some cases where you really want this to always be 4 and you want to protect yourself from the mistake of, I don't know, specifying more on the right. And this way you won't make a mistake. But maybe sometimes it really doesn't matter. You need a number of values. You don't even want to bother counting. So you just do that. All right. Good. And then we discard both of them at the end, and we can see that we can fit them in one line thanks to the semicolon. All right. Okay. I really like that little snippet, and it tells a lot. So now we should notice that in the object ls, I am not explicitly specifying the size of the array inside of the brackets. Instead of using literal value, like the value 4 that I used in the ns object, I'm using the special character underscore. This syntax tells the Zig compiler to fill this field with the number of elements listed inside of the curly braces. So the syntax is for lazy or smart programmers who leave the job of counting how many elements there are in the curly braces for the compiler. It's worth noting that these are static arrays, meaning that they cannot grow in size. Once you declare your array, you cannot change the size of it. This is very common in low-level languages, because low-level languages normally want to give you, the programmer, full control over memory, and the way in which arrays are expanded is tightly related to memory management. So this already tells me that, because we can define it like this, we don't need to deal with any, Zig style, in a initial, on the main page, we saw that, hey, we needed to pass some allocators here and there in that main example to make like a list or something, right? And that list was, I guess, growable. It was dynamic. We could grow it over time because there was some kind of loop for it. Here, we don't have to pass an allocator, so this is probably allocated on a stack, right? So if I'm gonna make a super large array, it's gonna be all on the stack, and I need to suddenly be careful, like, hey, don't make it too large, because, you don't want to go near Stack Overflow. Okay. So this is great. Selecting elements of the array. One very common activity is to select a specific portion of an array you have in your source code. In Zig, you can select a specific element from your array by simply providing the index of this particular element inside brackets after the object name. In the example below, I am selecting the third element from the NS array. Notice that Zig is a zero-index based language like C, C++, right, Python, and many other languages, really most any other languages. To the point where if it was one base, it would be weird. All right. Constant, NS, we have basically the same array. Try standard out print, and we print D will be probably for a digit. No, D for decimal. Yeah, I guess D is for decimal. And we just provided that one argument, right? NS and element number 2, which is really the third element. So it'll be 12, right? Yeah, there we go. Awesome. Span says, what language uses one based index besides Lua? One language that you might be somewhat familiar with. Bash. Actual Bash uses one indexed arrays. It's infuriating. In contrast, you can also select specific slices or sections of your array by using a range selector. Some programmers also call these selectors of slice selectors. And they also exist in Rust and have the exact same syntax as in Zig. And they also, I believe, exist in Nim, right? Anyway, a range selector is a special expression in Zig that defines a range of indexes. And it has the syntax start.n. Okay, this is very familiar syntax. So in the example below, at the second line of code, the SL object stores a slice or a portion of the NS array. More precisely, the elements at index 1 and 2 in the NS array. Okay, the question is, does it really store those elements, or does it only point to them? I would really like to know. When you use the start.n syntax, the end tail of the range selector is non-inclusive, meaning that the index at the end is not included in a range that is selected from the array. Therefore, the syntax start n actually means start.n minus 1 in practice. Okay, all right. So it will be from 1, which will be here, to 3, which will be 2. Wait, 1 to 3. So 1 to 2. Okay, so 1 and 2. Okay, all right. Kind of makes sense. So CPN says point to them. Doesn't make a copy. Awesome. That's what I am very happy to hear. So if that's the case, what happens if my function creates some kind of array, right? And then returns a slice? You exit the function, right? I guess this should be deleted because it was on a stack. We exited a function, therefore it went out of scope. By passing this, I presume we're passing these by value, therefore, we're just creating a new copy of that struct. How does it know where to look at? Does it magically hold the value somewhere? Lots of questions here if that's not a copy, but it's a reference, huh? Not even reference, just, points at it. You can, for example, create a slice that goes from the first to the last element of the array by using 0 to array.length. Okay, syntax. In other words, it's a slice that assesses all elements in the array. Bam. CBN says it holds the address of it. But this will stop existing, so therefore, if we're gonna return that slice, it'll be just invalid by the time we return it? I want to try it. So let's say that I'm gonna empty it all. Okay, this will be our main function, but we'll also define some public function get numbers. Okay, I'm not gonna specify what it returns yet because I don't know how to specify it. But let's say I'm gonna say that we have a constant numbers. And that will be, what was it, square brackets? Yeah. Square brackets, so we'll have, let's say, 5 elements, okay? This will be U16 or something, and we're just gonna say this is 4, something like this, something like that, and this, and that, okay? We've got 5 numbers. It inferred correctly. So now I want to return, and we were doing the slice of name of it with the stuff. So it will be numbers, and we're gonna return from 1, 2, 3. Why not just like that? And this now complains that, hey, the return type, expected return type expression. So I guess we need to do this, and somehow we have slice or something. I'm intentionally not looking what CPN is saying, because he's gonna tell me the answer that I want to learn by myself. So let's just get this guy. And how do I specify return type in a function in Zig as a slice of a specific array? And I already have like a bunch of ideas of what could happen here. Oh no, I have like extended thinking enabled. It's gonna take forever. Okay, so it would be, a constant array. So we're returning an actual array? Really? So let's do bam, constant U16. I guess no colon here, right? So that works, kind of. It doesn't show any errors. Now, before I look into chat, I'm going to quickly say, what was it, standard? Oh, we probably can't print it out, but let's say, variable ABC is get numbers, and that will be unhappy because it's unused. So we're gonna say that ABC is I don't know. I guess I need to make it a constant, right? And then we're gonna discard ABC. And that hopefully can compile. I mean, it compiled somehow. Let's get rid of the release. We don't need that anymore. Yeah, it compiles. So let's see. CPN says that's an illegal behavior. Yes, you'll get a segmentation fault. I mean, I would expect that it's going to protect me from segmentation fault. I mean, I didn't read it, right? I just saved the value somewhere. Can I just do something like standard debug print, and we're gonna say value 2 is, and this will be a decimal, and args will be, what was it, dot something, and we're just gonna say ABC dot, I know, second number. Save it, run it. Panic, index out of bounds, index 2. Oh, sorry, it probably has only 2 elements. So let's try that. And value 2 is 3413. So what I'm expecting is, because the constant value, it did some magic in there. If I would say var ABC is this, I probably can't change ABC. 0 is 12. Oh, it doesn't complain? Really? Now it complains. Cannot assign to constant. Okay, because it's a constant of U16. Okay, there's a lot of unknowns here. A lot of unknowns. CPN was like, what the hell? Yeah, this is fun. So how about we make it a var? And because, yeah, let's make it var and see if it allows me to compile. Now, when I compile it, cannot assign the constant. So it, again, just complains about this part. Can I make it not constant? Considering that this is just var? I can. And I can change the value. Okay. So if I'm gonna print it after the fact, let's say I'm gonna change this one to 12, it should change, right? Let's just add /ends at the end. Yeah, okay, so we changed the value of this thing. What if, after the fact, I'm gonna say ABC is, again, get numbers, and print it once more. I presume it's gonna get back because it's gonna get reinitialized here. Yeah, it went back. Interesting. SPN says, I'm confused. I gotta investigate. Well, there you go. Ben's breaking things. So how on earth does it work? Because my understanding is that we do get numbers, right? We are in our code here. We go here. We call get numbers. So we jump here to the scope. We create a variable numbers. Okay? We get a slice of it, which in my brain is, hey, this is a slice. We just start here and point at it. And then we return it. Therefore, the moment we exit out of here, back here, this should be discarded because it was on a stack, it's not anymore. So something indicates that either this is magically remembered, which I doubt, or this isn't really a slice, this actually copies the value? Huh. Let's see if we'll learn about it. CPN says you can print the whole array in one go. Any, and just provide the array. Okay, okay. I like that. So everywhere, we're gonna do array is any. And we throw in an entire array. What happened here? Paste. Pasting seems broken. Okay, it works. Beautiful. What just happened? That's not what's supposed to happen. If we're print out ABC, we get confusing values. At the same time, if we're gonna use the old way, okay, this is getting more and more interesting. So let's also do value 1. What's going to print out now? So it holds value 1, holds value 2, but when we print them out, why did the values change? Because that was never it. if I'm going to hide anything, will it work correctly? What just happened? Okay, the program stopped working. We broke Zig. I mean, I didn't change anything here. Let's bring it back to what it was initially. Now it works. But the moment we print the first value, it just freaks out. Spian says, I think that slice is pointing to a memory you don't own. I think so too. The moment we start printing out more, it just keeps changing. By accident, it was still holding this value because initially we went down the stack. So somehow this was pointing at a memory in the stack that was still there, right? We were able to print it. But the moment we put this thing here, the print, it does something with the stack, and therefore by the time it returns, we get a different value. So that's probably what it is. So yeah, you can still do dangerous stuff, no problem. Compiler won't stop you, so this is fun. All right. Be careful of your slices. Yeah, I would expect the compiler to actually not let me return a slice to something that does not exist anymore, but I guess it lets you, so that's kind of nice superpower. So yeah, NCBN says, Birdback got a bit busy. Alrighty. Okay, so let's just ignore the shenanigans that we uncovered and let's return back to normal learning. Okay, so we got that part. You can, for example, create a slice that goes from the first to last element. So we just learned that we can get a length of array by just name of array dot length, okay? And no parentheses required. You can also use the syntax start in your range selector, which tells the Zig compiler to select the portion of the array that begins at the start index until the last element of the array. And in the example below, we are selecting the range from the index 1 until the end of array. Okay, makes sense. We just leave out the other one. Can we do the other way around? Because, you know, here we're saying from 1 to 3, from 1 to end. Can we do this? Select everything? No. Select till number 2? No. Okay, so we have only the syntax from an index to somewhere, not the other way around. All right. Too bad. Okay, more on slices. As we discussed before, in Zig you can select specific portions of an existing array. This is called slicing in Zig. Because when you select a portion of an array, you are creating a slice object from that array. A slice object is essentially a pointer object accompanied by a length number. The pointer object points to the first element in the slice, and the length number tells the Zig compiler how many elements there are in the slice. Okay? Slices can be thought of as a pair of the pointer to the data, of type T, and the U size, the element count. Okay? Through the pointer container inside the slice, you can access the elements or values that are inside this range or portion that you selected from the original array. But the length number, which you can access through the length property of your slice object, is the really big improvement over C arrays, for example, that Zig brings to the table here. Because with this length number, the Zig compiler can easily check if you are trying to access an index that is out of the bounds of this particular slice, or if you are causing any buffer overflow problems. In example below, we access the length property of the slice, which tells us that this slice has 2 elements in it. Okay, there we go. So slice the length will tell us 2. Okay, this is awesome. We can, protect ourselves. All right. So then we have array operators. There are 2 array operators available in Zig that are very useful. The array concatenation operator, the double plus, and the array multiplication operator, double asterisk. As the name suggests, these are array operators. Okay. We saw them in those Ziglings tutorial. One important detail about these 2 operators is that they work only when both operands have a size or length that is compile time known. Okay. We're going to talk more about the differences between compile time known and runtime known in section 311. So that will be probably 30 streams later, considering how long this book is. But for now, keep this information in mind, that you cannot use these operations in every situation. In summary, the plus plus operator creates a new array that is the concatenation of both arrays provided as operand. So the expression A plus plus B introduces a new array which contains all the elements from arrays A and B. Okay, so this is basically only on the static arrays, right? We have a constant A as this array and B another array, and we can create a C, and they are all independent. Okay. So even if we would make it a variable, variable instead of a constant, it would still be, length will be known at compile time because we can't change the length on the go. I think. Because when we assign this thing here, right, this array, even if we'll make underscore, this gets a type of array of U16s that has a length of 5, even though it's variable, right? So you could assign it completely new array, but it still needs to have 5 elements. Okay, and here we have the way to print the array. All right, that works. Cool. So, so this plus plus operator is particularly useful to concatenate strings together. Strings in Zig are described in depth in section 1.8. In summary, a string object in Zig is essentially an array of bytes. So you can use this array concatenation operator to effectively concatenate strings together. In contrast, the double asterisk operator is used to replicate an array multiple times. In other words, the expression A multiplied 3 creates a new array which contains the elements of the array A repeated 3 times. Okay, again, it copies it. Alrighty. So runtime versus compile time known length in slices. Wow, they just said they won't explain it. And now we start explaining it. we're going to talk a lot about the differences between compile time known and runtime known across this book, especially in section 311. But the basic idea is that a thing is compile time known when we know everything, the value, the attributes, and the characteristics about this thing at compile time. In contrast, a runtime known thing is when the exact value of a thing is calculated only at runtime. Therefore, we don't know the value of this thing at compile time, only at runtime. We have learned in section 161 that slices are created by using a range selector, which represents a range of indexes. When this range of indexes, for example, both the start and the end of this range, is known at compile time, the slice object that gets created is actually under the hood just a single item pointer to an array. You don't need to precisely understand what that means now. We are going to talk a lot about pointers in chapter 6. For now, just understand that when the range of indexes is known at compile time, the slice that gets created is just a pointer to an array accompanied by a length value that tells the size of the slice. Okay. Very, very simple. If you have a slice object like this, as in a slice that has a compile time known range, you can use common pointer operations over the slice object. For example, you can dereference the pointer of the slice by using the dot asterisk method, like you would do on a normal pointer object. We haven't learned about pointers yet. So constant array 1, it's an array of 10 U64s. Okay, bam, we've got 10 of them. This slice has compile time known range because we know both the start and the end of the range. Exactly, 1 and 4 are known. On the other hand, and here's Tom. Hello, Tom. The issue you had with the return slice is apparently because you would normally pass an allocator or a buffer to persist the values between scopes. Yeah, normally. But the thing is that we're creating we're not creating just a normal array, we're creating a static array that lives on a stack. Therefore, we don't need the allocator, right? Because stack is cleared automatically the moment we exit the scope. That's how I would expect every normal language to work. So the moment we exit here, the numbers, this gets removed from the stack, as in, the data is still there. It's just ready for reallocation, right? That value is then, so whatever next will be assigned, we'll override it. And Dom says, yeah, so then you have undefined behavior. Yep, I just did not expect to get to undefined behavior so quickly. So it's just funny. I like that there's a way to do that. I mean, I can't see any legitimate use case for that, but yeah, it's possible. Function get numbers, allocator, standard mem_arg allocator, and then you can do exclamation mark and use 16 const numbers, try allocator. Holy moly. Complicated syntax. But yeah, I can see, at that point you allocate in a heap, and therefore you have the slower memory, or just more dangerous because it's on a heap. But yeah, I guess I just tried really hard to, hey, whatever I made here isn't really a scenario you want to replicate it in the first place, because, I mean, what's the point? I don't know. But at the same time, I can see some weird cases where somebody I made this little thing that can be used. It's a constant, so it's going to be shared and whatnot. But yeah. I mean, one could do this, right? Let's say constant numbers, and we just specify this, right? We have a global one. And then we just return a slice of numbers from whatever, 2 to 4, right? And at that point, it's all gonna work flawlessly because that data, that slice will be pointing to something that I guess is on a stack, but it's just, its scope is throughout the entire file. I don't know if we can export something like that with something like public, but that will work at the point. I would expect the existence of that is actually entire program, because something tells me this does a very similar thing to C language, where just copy paste the code, whatever, into like one gigantic file or something. But that's an assumption. So I could run this, and I mean, this won't work because I'm trying to reassign it. So it's gonna be like, oh, sorry, function return type declared here. Cast discards const qualifier. Yeah, so this needs to be const or some other way around. I guess something of this sort. And that will suddenly make these unhappy, so we can just say, hey, whatever, from this point we don't care. We'll just say that this is a constant. Yeah. And we used it here, so this should run now. Okay, there we go. And we can display the whole thing normally. Lovely. Alright, and CPN says, it's not dangerous, you just shouldn't forget to free it. Yep. And Tom says, it does seem strange there's no warning for the case you made. Yes, that was the first thing I was surprised, like, really, you don't track that this pointer points to something that's not going to exist anymore in literally next line. But hey, this is a young language. Not everything can be taken care of. That's even after what, 50, 60, I don't know how many years that is that C language exists, probably something like 70, 80 years. They're still working on a compiler, right? Still adding edge cases, adding this and that. Okay, so we learned a little bit about those slices here, single them. Okay, if you don't need to precisely understand what that means now. We're going to talk about pointers in chapter 6. For now, just understand that when the range of indexes is known at compile time, the slice that gets created is just a pointer. All right, accompanied with this. If you have a slice object like this, so yeah, we already went through this. Yep. On the other hand, if the range indexes is not known at compile time, then the slice object that gets created is not a pointer anymore. And thus, it does not support pointer operations. For example, maybe the start index is known at compile time, but the end index is not. In such case, the range of the slice becomes runtime known only. In the example below, we are reading a file and then we try to create a slice object that covers the entire buffer that contains the contents of this file. This is obviously an example of runtime known range, because the end index of the range is not known at compile time. In other words, the end index of the range is the size of the array file contents, right? Oh wow, this is a longer example. However, the size of file contents is not known at compile time because we don't know how many bytes are stored inside the shopless.txt file. And because this is a file, someone might edit this file tomorrow and add more lines or remove lines from it. Therefore, the size of the file might vary drastically from one execution to another. Now, if the file size can vary from one run to another, then we can conclude that the value of the expression file contents.len exposed in the example below can also vary from run to another. As consequence, the value of the expression file contents.len is runtime known only, And as a consequence of that, the range 0 to file contents.len is also runtime known only. Okay, so let's look at how we deal with files. Constant standard, import standard, constant built-in, import built-in. Okay, so we've got something built in. That's interesting. So we have a function that we define first, read file. It takes a magical allocator and a path, which is, I guess, a string. It takes a slice, okay? So I guess this thing represents a slice. And returns possible error and another string. Just not constant anymore. And then we have constant file, try. So we create a file, whatever, we just open it, right? So we get an handle to file, or I don't know how it's called in Linux. So standard file system, current working directory, I guess. Open file to the path, and that's it. No extra arguments. Excuse me. So we ensure that eventually the file will get closed, and then we try to file reader, read all alloc, allocator, and standard math max int usize. Okay, so I guess read all alloc basically says that, okay, we're going to read into the allocator, and how much? As much as we can. So I guess till the end of the file. And this would be max int of usize, so yeah, a lot. And we'll return what we just read. Okay, so that's gonna be just a string. Okay. So then we have function main, which can throw. So GPA is a general purpose allocator, okay? All right, so we have standard heap. Oh, interesting. So what is under standard heap? I'm instantly curious. Standard dot heap. We have query page size. Oh, the default implementation of standard option queries page size asserts that the page size is within page size min and max. Ooh, interesting. So I guess these are the pages that everything's aligned to or something. Memory pool aligned, test allocators, and a bunch of other stuff. Okay, not a ton, but very alien things. So we get a general purpose allocator. We create an instance of an allocator here. So I guess here we just imported. I have no idea why it's two-stage, but whatever. I guess maybe we can configure it further before we actually create an instance. Maybe. So then we specify the path. It's constant, so it's all happy. And then file contents, read the file, we provide a constant path, and we get the file contents, which is just like an array of U8s, array of bytes, which is the same as string, I guess. And we get a slice from 0 to the end because we get file contents.length. So yeah, this is definitely runtime stuff. Yep, and we just discarded because why not? We did all this work for nothing. All right, I'm understanding. Somewhat. So let's go to blocks and scopes. And blocks are created in Zig by a pair of curly braces. A block is just a group of expressions or statements contained inside a pair of curly braces. All of these expressions that are contained inside of this pair of curly braces belongs to the same scope. Yep, makes sense. In other words, a block just delimits a scope of your code. The object that you define inside the same block belongs to the same scope, and therefore are accessible from within the scope. At the same time, these objects are not accessible outside of the scope. So you could also say that blocks are used to limit the scope to the objects that you create in your source code. In less technical terms, blocks are used to specify where in your source code you can access whatever object you have in your source code. Alrighty. So a block is just a group of expressions contained inside of a pair of curly braces, and every block has its own scope separated from the others. The body of function is a class example of a block. If statements, for and while loops, and any other structure in a language that uses the pair of curly braces are also examples of blocks. Can we create our brand new block just by curly braces? Because I would say it should be possible that we just do this and do whatever. Constant high is high, right? And then we just discard it. Yep, it works. We don't need to have an excuse like a function to create a block. We can just create it. This way we can do a bunch of stuff and our stack gets cleaned up, right? So that we don't have issues with, growing through a long function. This means that every if statement or for loop, etc., that you create in your source code has its own separate scope. That is why you can't access the objects that you define inside of your for loop or if statement in another scope. For example, is code outside of the loop. Because you are trying to access an object that belongs to a scope that is different than your current scope, you can create blocks within blocks with multiple levels of nesting. You can also, if you want to, give a label to a particular block with the colon character. Just write label before you open the pair of curly braces that delimits your block. When you label a block in Zig, you can use the break keyword to return a value from this block, like as if it was a function's body. Oh, you can just write the break keyword followed by the block label in the format label. An expression that defines the value that you want to return. So we can have variable y is 1 to 3. Then we have constant x, which is add 1. Oh, so this is our label. So, all right. This is fun. So we create a label and a block. We do some calculation, like increase the x, the y, and then we break into the add 1. We break this block by providing the value 1, y. So we just increase the y by 1 and then assign the value to x. Interesting. So I guess you can do that only with break. And then we have this thing like, hey, blah, blah, and it should be 124. All right. Huh. This is interesting. Huh. I like those weird things. So this was an example where we had something of this sort. Okay, and we are missing the y. Let's just copy the whole thing, all right? This way we have the entire example. So yeah, all that is fine. And then we have constant this. But can I just do break? No, break can be only used within a loop unless we have the actual scope. So something tells me there's some kind of convention that maybe everyone says, I know X or maybe B for block or something, and you have something short. I don't think you can do underscore, right? Oh, you can. Oh, that's fun. Okay. I did not expect that to work. But maybe that's the way to do it, right? If you want to do some more advanced calculation to do that, interesting. CPN says block expressions are cool. Yeah, very interesting to see block expressions like that in a low level language for some reason. I know that Nim has them, like, we can do a lot with them. But Nim is Nim, Nim is overbuilt, right? So I'm just really surprised to see it here. Okay, so we have some hints about blocks and overall labels that we can just do some magic. We unfortunately have to have the syntax, because if we were to do return here, like return y, this says that it's unused, and this has a type of no return. So I guess this just returns from the entire thing. I like the type no return. But this makes it return proper value. Interesting. So it's just too bad you have to do this, but at the same time, not a big deal. Maybe there's a way to not do this. And CPN confirms that will return from the main function. Yep. All right. Alrighty, so how strings work in Zig? The first project that we are going to build and discuss in this book is a base64 encoder decoder. So that will be in chapter 4. Whoa, so we have a lot of time. But in order for us to build such a thing, we need to get a better understanding on how strings work in Zig. So let's discuss this specific aspect of Zig. SPN says, no, you have to use a label there. No other way. Okay, I can live with that. If I can use underscore, that's great. Strings in Zig work very similarly to strings in C, but they come with some extra caveats which add more safety and efficiency to them. Well, caveats doesn't sound like safety and efficiency. So I will say features. You could also say that Zig simply uses a more modern and safe approach to manage and use strings. All right. A string in Zig is essentially an array of arbitrary bytes, or more specifically, an array of U8 values. This is very similar to a string in C, which is also interpreted as an array of arbitrary bytes, or in the case of C, an array of character, which usually represents an assigned 8-bit integer value in most systems. I like the word usually in most systems. Now, because a string in Zig is an array, you automatically get the length of the string, as in the length of the array, embedded in the value itself. Exactly, that makes it safe. This makes all the difference. So this is exactly the same as in Nim language. String is literally just an array of bytes or whatever, U8s, with the length at the end. Yeah, embedded in the value itself. This makes all the difference, because now the Zig compiler can use the length value that is embedded in the string to check for buffer overflow or wrong memory access problems in your code. All right. To achieve this same kind of safety in C, you have to do a lot of work that kind of seems pointless. So getting this kind of safety is not automatic and much harder to do in C. For example, if you want to track the length of your string throughout your program in C, then you first need to loop through the array of bytes that represents the string and find the null element, okay, whatever, escape 0, position to discover where exactly the array ends, or in other words, to find how much elements the array of bytes contain. I mean, how many elements the array of bytes contain. To do that, you would need to do something like this in C. And in this example, the C string stored an object array is 25 bytes long. Okay, so we're gonna look at some C. And CPN says in C strings are null terminated. Exactly. So I include the standard library, int main, right? Same stuff. We create a pointer to a character, which will be our array, an example of strings in C. Exactly. It's just a pointer to where the array begins. And that's all we have to go on, where it begins. We track that our current index is 0. And then while true, we just keep going and checking, oh, is this character the end? No. Let's go to the next one. Is this one end? Yes. Okay, let's break. And we know that this index now holds the number of elements. Yeah, there we go. So a little bit more manual and just error prone. But at the same time, look how much memory saved. You're not storing the I don't know, you save a little bit of memory. I guess, because this is just a pointer to where the array begins. And because you don't store the length, this can be thousands or hundreds of thousands of characters. So it could, in theory, be a lot. While if you have it in Zig, so that one extra character at the end, the null terminator, is just 1 byte. But in Zig, that you need to store where the array begins and that extra value. But I think that at the end, because of how the system stores separate variables or whatnot, it ends up being exactly the same. That one extra character probably won't make any difference in 99.9% of cases. And Tom says that issue you found is apparently unsolved because to do it would require breaking one of the principles of no hidden allocations in a debug mode. Well, I guess I'll be going back to Java/Clojure. How would it break to no hidden allocations in a debug mode? I mean, solving it as making it work, I can see yes. Forcing it to just magically work, 100% that would be breaking it. And I wouldn't want it to work because that would feel like that shouldn't work. But having an error as in like compiler to catch it, yeah, that would be great. Like, hey, you're trying to send a slice to something that's in the local stack outside of the scope of this function. I know nothing about how compilers work, but it sounds like not that difficult. I don't know. It's probably on the to-do list. It's just to-do list. It's probably like 200,000 items of all the edge cases that the compiler needs to catch. All right. So yeah, that makes sense. The code makes sense. It's actually surprisingly readable because it's so standard. You don't have this kind of work in Zig because the length of the string is always present and accessible in the string value itself. You can easily access the length of the string through the len attribute. As an example, the string object below is 43 bytes long. So a constant standard, right? Standard out, and we create some kind of writer to the standard out. So I guess this will be just to be able to print out. And we have our function. So constant string object. So this is an example of a string literal in Zig. All right. And how many characters is that? Let's do, what was it? This thing, and I guess I can pipe it to, what was it? WC? No such file. Echo. Sorry about that. 44 characters. Okay. So this is 44 characters. This is supposed to be 43. What? Did I copy something extra? I mean, that'll be escaping it. This should, yeah, 44 characters. Huh. Why is the 43 in here? So standard out, print this thing. And it says 43. String object length. I must have screwed something up. I need to count myself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 40, and 3. Okay, my word count on Linux is lying to me. Alright, so it is 43. And prints it that, okay, length is 43. But can we get like a size of an object that will tell us? Sonnet, not thinking. How can I get a size in bytes of a variable in Zig during runtime? Hopefully. I don't know if it's possible. Size of built-in function. So basically, we have something, right? Size of, type of this thing. Oh, that's a type of. Get size of variables type. Oh, okay. So where to go? We have this thing. I want to copy it. I'm gonna wait. This doesn't have. This has a main function. Beautiful. So we're gonna do this thing and let's do length, right? And then we're gonna do size is another thing and bytes, I think. So the first one will be this. The second one will be at size of, and we do another at type of. So interesting. This one is lowercase. This one is uppercase. Uppercase because what? It's static or something? I don't know what it means. Type of string object. What the hell is it gonna tell us? Ooh. Struct declared here. So root source file struct IO has no member name, get standard out. Oh, this is like the old way of doing things, right? So instead of doing this whole standard out writer, we haven't learned that yet. We're just gonna do std.debug print, right? It should be the same thing, basically. Oh, and CPN, wait, what's going on here? Tom says, yeah, the creator wanted to add it, but it got pushed back. Okay. Echo is wired. Weird. Okay, yeah. Spin size off. Change that to standard FS files std out. Deprecated writer. Okay. Function names are camel case. Okay, function names are camel case. So this is a function, but what is this then? If it's starting with capital, they're both built in, right? Start with some at. I guess at is called the built-in. I don't know. But this should work. The debug print, right? So let's try new, and we've got more errors. Beautiful. Expected error union type found void. We're not throwing errors. Oh no, what did I just do? Control W to close it, right? Oops. Okay, we're going further. Consider omitting try. Yes, because we have debug, we have so many leftovers from other stuff. There we go. Size is 8 bytes, but it doesn't tell us how much the entire thing is. Type names including functions that return a type or Pascal case. Okay, so I guess this is like, if this returns a type, that means that it's supposed to, I guess, point it out to you like, hey, you probably want to be careful with this thing or something. Can I just do size of an actual object or something? No, it expected a type. So, while did this thing give me answer for different variable types? Yeah. Key points. Type of. This only returns the size of a type, not the entire array with all its elements, length, tracking, pointer data, etc. Of course I'm right. Different scenarios. Array versus slice behavior. Okay, this is just getting nowhere. Yep, this is going nowhere. Nope. Total memory footprint. And it just hard codes stuff. So no thank you. And I guess using an allocator would be probably a little bit more helpful because you could probably track it to some extent. Interesting. I guess we'll learn over time. And Sven says just multiplies those two. Yeah, I mean that will be multiplied, but I'm curious, like, what is the actual footprint in memory? Like, what does it actually take up in memory? Like in practice and physical, not just in theory. Because it was said that hey, the string contains its contents, right? But also it contains the length, right? How many bytes does that take? Also, us holding the pointer to that variable in memory is another piece of data. So yeah, there's like, I want to see how much total does this thing cost me. But I guess this is a rarely used case scenario. People prefer to think about it probably. All right. So we go through this, all right? This all makes sense. Okay, another point is that Zig always assumes that the sequence of bytes in your string is UTF-8 encoded. This might not be true for every sequence of bytes you're working with, but it's not really Zig's job to fix the encoding of your strings. You can use iconv for that. Okay, so I guess this is a library that can verify if whatever your runes or whatever you call them are all correct. Today, most of the texts in our modern world, especially on the web, should be UTF-8 encoded. So if your string literal is not UTF-8 encoded, then you will likely have problems with Zig. Okay. And Sven says try size of U8 as an array. But I think that's what we're passing here, because type of string object is that thing, right? So let's do an array of U8, which will be U8. Now it's 16 bytes. Okay, that's better. if we're gonna give it one element inside, is it gonna be more or less? 1 bytes. Okay. I did not expect that value. So I guess the real value is this plus, in this case, 43 of those, which will be string object length here. And this will be the real value, right? 59 bytes. Because we have 43 plus the 16. I guess the 16 is for the length of a string. That's lots of bytes for that. Don't know. It's a mystery for now. All right. Okay, so let's take, for example, the word hello in UTF-8. This sequence of characters, HELLO, is represented by the sequence of decimal numbers. Bam. In hexadecimal, the sequence is bam. So if I take this sequence of hexadecimal values, and ask Zig to print this sequence of bytes as a sequence of characters, as in a string, then the text is hello. Then the text hello will be printed onto the terminal. So yeah, you just make integers, all right, mark them as U8, and ask to print them as a string with this S little thing here S. It will just print them as a string. There you go. So I guess this would work the same way if I did the inverse, right? We're gonna go down here and we're gonna say our bytes will be Walala, right? And if we're gonna take our bytes and we're gonna say, hey, these are decimal, we need to do std debug print. There we go. It will just say a bunch of numbers. Valid format string D for type something. I guess we cannot say decimal because this is just random. Yeah. Any? There we go. It printed it out. Okay. Lovely. And CPN is right there with change S to any. Yep. Alrighty. So we figured that out. So we're nearing the end of this whole article. No, we completed like 70% of it only. Wow. Whew. I guess we're gonna finish the introduction to Zig and maybe do a few Zigling things and we'll be done for tonight. Wow, this is going slow. But at the same time, I'm reading the book aloud and experimenting, getting weird stuff. So no surprise here. Using a slice versus a sentinel terminated array. I guess the terminator is the sentinel. In memory, all string values in Zig are always stored in the same way. They are simply stored as sequences of arrays of arbitrary bytes. But you can use and access this sequence of bytes in two different ways. You can access the sequence of byte as a sentinel terminated array of U8 values, or as a slice of U8 values. Okay? So what the hell is the sentinel terminated arrays? Sentinel terminated arrays in Zig are described in the language reference of Zig. In summary, a sentinel terminated array is just a normal array, but the difference is that they contain a sentinel value at the last index element of the array. With the sentinel terminated array, you embed both the length of the array and also the sentinel value in the type itself of your object. Okay, So that probably explains why the array was 16 bytes. Because when I think about it, 8-bit is what? 1 byte. 16-bit is 2 bytes. 32 bits is what? 8 bytes, right? So we have two 32-bit values. One is the sentinel, and one is the length. Therefore, we get 16 bytes to actually store the array. So maybe that's the answer. Maybe. And CPN says no. That 16 is from 8 for the pointer and 8 for the length. So inside the array itself, we're pointing pointer to it? Because as far as I know, if I create an array, which I don't have now, let's say that this is my array, right? This is my array. This is the pointer. This is the value. Therefore, I expect that this is the pointer, and this itself doesn't have a pointer to itself because this points to the whatever there is, probably length and then sentinel and then the values. Pointer points to the first element, yeah. But this is the pointer on the left side. The moment we lose this pointer, this data, nothing has access to it. But maybe I'm wrong. I don't know. It just doesn't make sense that this would hold a pointer to itself. SPN says it's pointer and length, aka fat pointer. Oh, so you're saying that the data lives somewhere, right? And we just have this points to the fat pointer that points to the actual data lives somewhere. Okay, so we have like that's what we're doing on a stack? Really? That sounds so wasteful. There must be difference between how it's being handled on a stack and on a heap. I don't know. It's weird. Huh. Very interesting. Very interesting. Okay, so the sentinel value is some kind of combination of what the, like per type, what the sentinel value is. For example, if you write a string literal value in your code and ask the Zig to print the data type to this value, you usually get data type in the format of star constant, so I guess pointer, constant pointer to this thing. The n in the data type indicates the size of the string. That is the length of the array. And the 0 after the n part of the data is the sentinel value itself. Oh, so basically there's null terminator, right? So this is a string literal value. Bam. Try standard out print and type of a literal value. What's the point of this? Constant 15 0 U8. So what? So you're telling me that in addition to null termination, we have the length, right? So we have both at the same time. Interesting. And SPN says asterisk const just means whatever the pointer is pointing to is a constant. Okay. Thank you. So with this data type, bam, you are essentially saying that you have an array of U8 values of length n, where the element at the index corresponding to the length n is in the array is the number 0. if you really think about this description, you will notice that this is just a fancy way to describe a string in C, which is a null-terminated array of bytes. The null value in C is a number 0. So an array that ends in a null/0 value in C is essentially a sentinel-terminated array in Zig, where the sentinel value of the array is the number 0. So I guess they're doing that purely for to cooperate with C, right? Because I think nym does the same thing. Therefore, a string literal value in Zig is just a pointer to a null-terminated array of bytes, for example, similar to C string. But in Zig, a string literal value also embeds the length of the string. Also, the fact that they are null-terminated into the data type of the value itself. Okay, a little bit confusing here, but great. Sure. How can we control the null termination ourselves? That's the question. Okay, so slice. You can also access and use the arbitrary sequence of bytes that represent your string as a slice of U8 values. The majority of functions from the Zig standard library usually receive strings as inputs as slices of U8 values. Slices were presented in the section 1.6. Thus, you will see a lot of string values with the data type of array of U8 or constant array of U8. But no, array will be this larger thing, right? We need the length and the terminator. Well, this one has no length at all. Depending if the object where the string is stored is marked as constant with const or variable with var. Now, because the string in this case is being interpreted as a slice, this slice is not necessarily null terminated because now the sentinel value is not mandatory. Okay, you can provide it, but it's not mandatory, huh? You can include the null 0 value in the slice if you want to, but there is no need for it. So this is a string value being interpreted as a slice. So a string, and so we have a string value, right? But we say it's a constant array of U8. So therefore it's a slice already. And then standard out print. So we print it as any and type of it. And it's a slice. Okay. Okay, that makes sense. So I'm just gonna take a short bathroom break and I'll be back in 2 minutes. All right, I'm back. And I just remembered something that just makes me laugh. So the Zig logo for some reason, that logo itself, without the word Zig, for some reason, it just, every time I see it, it reminds me of a sports drink. Just very specific sports drink that just brings to my mind. Where do I have it? Because I actually asked ChatGPT to help me out with this. This is what I see when I see Zig logo. Just it just makes me laugh. All right, where are we? Breakfast matter? No, not right now. It's not time for breakfast. There we go. So, yep, Zig energy. Yep, that might be it. I might one day make a splash screen for bathroom break, or a splash screen for when I'm going to get a drink, and there's me drinking from it. So, yep, it's just funny. It could be like, you know, another mascot, because then when I think about it, those mascots in Zig, it's an iguana, right? But for some reason, when I look at them without knowing that it's an iguana, they look like alligators. Like an alligator is just a logo of whatever, a mascot of Zig. And that's that. Oh, Travis says, "Hey, I'm back. How's it going? Have you written on a Zig yet?" Yes, we broke the compiler, as in undefined behavior, because I'm poking too hard. So yeah, that was fun. Not a lot of writing. I guess I'm just trying to finish that first introduction to Zig, and then I'm gonna do some Ziglings. Learning a lot about stuff, being confused about a lot of stuff, and, you know, null terminators and stuff. What is the actual size of the value of the array and all that stuff? It's hard to, yeah. Did you get a stack trace? No, actually got an undefined behavior, as in I can read the data that isn't mine to read anymore. And did it make sense? Yes, it did make sense. Absolutely. I mean, I can show you if I can remember it. It would be good exercise, right? The whole idea is that we have a function, or like function, let's say get number. And this is going to make you very, very upset, because we're going to say this is a variable, and we're going to say numbers, and this is going to be straight up a list of numbers, okay? 1, 2, 3, 4, 5. Maybe 6, 7, 8. Nothing crazy here. But what then we're gonna do is return numbers from, let's say, 2 to 4. All right? And we're gonna say the return type is a slice of U8. Something like that. U8. Sorry, ... There we go. When you look at it, you're probably like, oh no, what on earth? And the compiler will be angry. But no, the compiler isn't angry. You probably encountered it yourself, but I can easily say, hey, standard debug print. Let's just reuse this thing because it's a pain to write. You know, print the get number. Or we can even better, var nums is get number. Okay, numbers, even better. And we're gonna print it, right? We're gonna print it as nums. Or maybe we want to print the first one. First. And it's gonna be nums 0. That's gonna be fine. The moment we're gonna print number 2, it's gonna screw itself, right? And this is gonna be all wonky, and we have no problem also doing something like numbers. Let's say first element is this. I mean, it won't fit in U8, but there we go. And I can do the same thing. And the behavior here will be, it works. Bam, there you go. So when we run it, the first element is 3, second element is 3. Let's rerun it. And array is 170, 70, and all that fun stuff. It's just like, oh, And Travis says, Zig is like C here, doesn't protect you from returning pointer to local. Yeah, there are proposals though. You understand why this happens? Yes, exactly. Because the way I understand it is that in here, the array that we're making, this is not something dynamically allocated on a heap. This is something allocated on a stack. Therefore, we allocate it on the memory. Then we create a slice, which just is a pointer to whatever, element number 2, and we have length of 2 elements. So basically like, hey, this and that. And therefore, we return it. By returning it, we're basically creating a copy of it, I would assume, which is a copy of the pointer and the length. Therefore, this holds a pointer to this. But because this just came out of scope, you know, it was on a stack. It got pulled off the stack, so, you know, it went backwards a little bit. And in theory, this element prints fine. But the moment we call print, it's basically like, oh, you know, the first, I guess, operation is that, oh, I'm going to extract that, put it on a stack so that our number 3 is safe. Then it's going to do a bunch of logic for print, which is probably putting a lot of values on a stack, prints it out. By the time it goes back, our array data is already overridden. That's how I understand it. And therefore, we get oopsies after that. But we can still modify it, so that's fun. Yeah, that will probably allow us to pass that slice into some areas in the code that go deeper into the stack, and then override some values of the code that is already running. Therefore, values that sit on a stack, and that could probably be really, really messed up. I don't know if any values of where to jump to after function and whatnot is stored in a stack as well, but if it is, it could be a disaster. And Travis says, yeah, get numbers. Stack gets reclaimed once it returns to main, and main is free to reuse it. You just get lucky it hasn't happened. Yep, exactly. If it goes on and I keep changing that, it would be like, oh, we have a weird situation here. Yep. And I wanted to share something because I don't know. Try this in release mode, please. I will. All right. Do we have it? Do I have it? Was it -O or something? What the hell? Zig -run. Oh, there we go. Of course, shortcuts don't work in VS Code. Yeah, and release mode is even weirder. Even the first element is wrong. I guess it gets cleared? Yeah, so in release mode, looks like after stuff in stack is deleted, it gets zeroed? Interesting. I would expect that behavior to be in debug, not in release, but okay. And then, yeah, then we start overriding it with leftovers. Okay. Travis says, no segmentation faults since it's legal to access that memory. You know, perfectly legal. CPM is saying, doesn't that slice point to reclaimed value? It does, right? Yep. I don't know what a segmentation fault is, though. Don't know how this works. 170 is OXAA. Zig usually sets undefined memory to that value. All right. And debug builds. Okay. Oh, that's why we get 170 everywhere. All right. That makes sense. So I guess for you, int, it's 170. Okay. It'll be different if we did. What was it that we were trying? Let's select our U8s. Okay, we have just 2 of them. And we're gonna make it U512, right? We run it. Not in a release mode. And we get, yeah, a bunch of big numbers. What was it I was doing? 64? Because that was like nice 2 number. Whatever. It changes. Depending on the value. Never mind. Doesn't matter. But yeah, Travis, I want to show you something, because every time I see the logo of Zig, I just have a specific energy drink in my head, like the sports drink. So I needed to visualize it, and that's what comes to my head. And that could be a new Zig branded sports drink. It just makes me laugh. Okay, so let's go on with continuing here. So we learned that we can define slices with this specific type. Okay. Okay, and this was an example that we can straight up say that a string is a slice without even, like getting a slice. We just said, hey, this is a slice, and somehow it magically works. I guess here Zig kind of infers that we intend to get a slice and says as a step. That's what I guess is happening here. And we can print it no problem. Yep, it's funny. It's just that lightning just, I don't know why I think about that. All right, iterating through the string. If you want to see the actual bytes that represents a string in Zig, you can use a for loop. So iterate through each byte in a string and ask Zig to print each byte as an hexadecimal value to the terminal. You can do that by using a print statement with the X formatting specifier, like you would normally do with the printf function. Okay? And see. So we have our standard. Again, we have the old style of printing out. And our main string object. So we have our string. And then we print bytes that represent the string object. And we have nothing, right? And then for string object, we extract byte, and we just print. I kind of like this syntax of a for loop. It's funny that we're going iterating through the string before we have control flow introduced, but whatever. So for string object byte, and then we basically print out that byte because it'll be just U8, and that's it. So bytes that represent the string object, bam. Okay, not sure why this example is here in the first place, but okay. And Travis says, segfault happens when you try to access memory you're not allowed to, such as memory that's been freed or outside of our. For instance, if you declare a runtime array of length n, and then you try to access n plus 1. Or if allocate some memory free and then try to access it. I guess this is because allocators, basically the role of the allocator is to request memory from the operating system. And therefore, if we try to access outside of that memory, the system will be, angry at us, right? That's what it is. Okay, so we have this thing, bytes that represent string, great. Okay, so a better look at the object type. Now we can inspect better type objects. We can inspect better the type objects that Zig create. To check the type of an object, you can use the add type function. If we look at the type of the simple array object below, you'll find that this object is an array of 4 elements. Each element is a signed integer of 32 bits, which correspond to the data type i32. And Zig, that is what object blah blah is. Okay. And Travis says, yes, correct. So Okay, so basically an allocator is intermediate to work with operating system, and I presume you could write your own allocator that, let's say, requests a larger chunk of data once and then manages it on its own whenever you use it to allocate this, allocate that, and this way you could reduce the seg faults, but at the same time shoot yourself in the foot if you have a situation where you did an oopsie. Is that correct? Because I'm trying to figure out, what's the extent of an allocator? Because is it like, are there situations where Zig is the one managing memory, or are there situations, or does it have to directly go always to the operating system every time you want to, make a little array? Because I'm thinking like, gosh, that's lots of system requests, and that will be, a lot of whatever context switching or whatnot. It just seems like unnecessary operations. So I can imagine, it working differently, because in our stack probably here, the why it didn't get errored is because we have stack pre-allocated of a specific size. So we have a chunk of memory that we can write to wherever we want to. And, this is no allocations because all pre-allocated is a big chunk and we can do whatever we want with it, I guess. CBN says, I always thought this is also the case for stack memory that is freed after that function has exited. And Tom has, I think that's why they have different allocator types. It depends on the implementation of the allocator. Okay. So Travis says, and others use it to allocate large chunks they manage. This way, they reduce syscalls needed to make things more efficient. Yeah, exactly. Okay, so I guess the generic one is just a dumb one. Or like the one that try to do the least, or maybe not, maybe it has some strategy there. Or you could have a different one that, you use specifically for having memory for a bunch of small arrays or whatnot. Okay, yep, I can see it. It's a cool idea to have those allocators doing different things. I'm sure C does something like that too. It just seems like it's like a actual first order feature or member of the language itself, rather than you needing to come up with your own solution in C. I guess that's how I would view it. Okay. Because in C you have memallocc and all that stuff, and I guess it's a little bit more manual. Okay. Enough of allocators. We learn about them in chapter 3, which will be 3 years from now. CPN, there's arena allocator for managing memory allocation efficiently and free all the memory in one go. Perfect. Yep, I can see that working. Okay, so better look at the object types. So we can get a type, right? And array of 32 bits. So I guess this is it, right? We have our simple array, which is supposed to be an array of 4 32-bit integers. And we print it here. Hey, type 1, type of simple array. And it should print out, okay, 4 of I32. So it's that simple. Okay. So each element is assigned integer, which corresponds to the data type in Zig. But if we look closely at the type of the string literal value exposed below, you will find that this object is constant pointer, hence the asterisk const annotation, to an array of 16 elements or 16 bytes. Each element is a single byte, more precisely an unsigned 8-bit integer. That is why we have the 160U8 portion of the type below. And also you can see that this is a null terminated array because of the 0 value after the colon character in the data type. In other words, the string literal value exposed below is 16 bytes long. So we have this string, right? It's a string object. We are forcing it to be a slice, though. This is a slice, right? This is syntax for a slice. So what the hell? This is not a normal string. I'll need to investigate that. We have string object. We print. Oh, okay. Here they're printing the actual string. Sorry. So that will be pointer constant to the so I guess array, and this is like the special syntax that, okay, this is array of 16 elements, but with the null terminator, right? So in theory, that will be 17 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it'll be 17 elements because we need to add that null terminator, I guess. What do we have here in chat? A lot. Travis says stack memory is a large static chunk of the program that the program gets, and it's always okay to access it. Yep, exactly. Yep, that's the stack. Stack is fun until you run out of it. I wonder, can programs actually request more stack memory? That'll be interesting, huh? SBN is asking, is that the case for stack memory with a function too? Yeah, function. So let's see what Travis says. Yeah, when you call a function, the compiler figures out how many parameters and variables it needs and allocates a bit of the stack to those. Then it returns that memory. Once again available to the caller. And CPN says, I'm not talking about kind of like small fixed buffer allocator. So let me show you something, CPN, because I think I know something, and we have an expert here, Travis, and maybe he can tell us if we're right. So Excalibur, prepare for whiteness. Let's skip that. That's a different live stream. Let's also copy some code, all right? We can actually use this fun thing, this little piece of code. We're gonna use that as an example. So we're gonna go here. I'm gonna place it as text, and we will walk through it the way the compiler sees. So when the program runs, okay, what happens is it will basically allocate, hey, the operating system will allocate, hey, here's your stack. This is your stack, this is what you have available. I don't know, it's a number of data, right? And Travis says, yes, you can segfault in Zig if you infinitely recurse. Yeah. There's only so much stack available, maybe 1 megabyte, I don't know. So let's say that this is our 1 megabyte here, right? It's not a gigantic number, so you don't want to put like a big arrays. So the way we started in our function main, right? We don't have anything here, so we started in function main. So I imagine that we have our stack. I'm gonna move it maybe this a little bit. There we go. And I'm gonna make a little arrow that points at what we're executing, okay? Can I extend it without attaching it to anything, please? Come on. There we go. So we start here, okay? And therefore, we are in function, we don't need to define anything here. We come here, and it's var numbers, get numbers. So what our program will do now, when it's executing, it sees like, hey, I need to go into get numbers because I can't assign anything here yet. I need to calculate this first. So what it's gonna do is like, hey, I need to go to get numbers. So maybe it was tracking that, I'm in main, okay? and then it adds to the stack. I don't know if it actually adds that to the stack, but let's pretend that it adds to the stack. Okay, now I'm in get numbers. Okay, it keeps track of it. It's just a value, whatever, a pointer. Or I would say that it actually tracks probably a pointer back to the main or something like that. So let's say in main, it doesn't do anything. When it goes here, it will basically be a pointer back to main. Okay, that's what it does when it moves to get numbers. So when it's in get numbers, it moves on to here. All right, let's execute that. It sees like, oh, we need to allocate a bunch of memory because we want to create an array. So it creates a bunch of memory for the numbers. And this is an array of what? 8 elements, right? And U64. So it allocated memory for this. It holds it there. Then it goes and sees return numbers, this and that. So it sees like, oh, before I return, I need to create those numbers. So it's gonna get the return value, right? And it's a whatever slice of U64, which is 2 values, right? So it created that. So now it's like, oh, okay, I have a return keyword. So what it needs to do is basically I guess it remembers that. What it does is like, okay, so I'm here now. I need to clean up whatever I hit here. So it's gonna straight up delete the numbers. So we're gonna grade them out. We can't grade them out. This, something like that. Okay, we have grayed out numbers. We don't have them on the stack anymore. And it puts that value somewhere here maybe. So we'll just for remembering, we're just gonna put it here. It's gonna write that, hey, now I'm using that pointer to go back to main, so it's gonna go back here. And now it has that return value, right? And it's gonna assign it to nums. So nums now holds this value, okay? And it overrode some of that stuff that was already back here because it just figured, I don't need it anymore, great. So the moment it goes here to print, it basically goes like, oh, I need to calculate num 0, so we're just gonna get num 0 is whatever, U64, right? And it holds that value and then calls the print. So again, gets the pointer back to main. We forgot to remove that, right? So I guess this was holding here, here, and here. And then it goes into print, declares a bunch of other little things in here, but by the time it ends the print, it just deletes this data and is back in here, can remove this access to nums as well, and moves on to the next piece. So it just kind of like constantly adds values, goes back, rewrites the values, goes back, rewrites the values. That's why when you have recursive function, what happens is that you have pointer to parent, right? Function, and it's gonna go in and okay, I'm gonna execute my stuff here, and another recursive will get another pointer to the parent and stuff, and another pointer, and it basically to the point where you're literally like, oh, I ran out of room here. I can't go and add more stuff to the stack. So you can think of if you didn't have that and it finished, all this stuff is gonna start getting deleted because, oh, we cleaned up and we went all over to here and we have the value, bam, bam. That's how stack works. Travis says, I'll be away from keyword for a bit, making food, and CPN says that function only takes that slice, pointer, and length, not the elements, to the main function, right? And CPN says, oh, okay, got it. Yep, that's all stack is just really nice and clean. That's why we don't have to manage the memory, because it does it on its own. It just does bare minimum. But you have the restrictions that everything needs to be the size that's roughly known or can be handled pre-compilation time. So you can't do any weird oopsies like, oh, I'm gonna get this thing that grows or something. You can't. You can pretend by making a big array that can hold some kind of values and then do a bunch of stuff, but that's just to avoid the heap, right? Alrighty, and that's why you have one block and you don't have to ever call to this operating system like, hey, create room for this and that. It gives you that chunk to work with to begin with. Okay, so we go back to the book and maybe, wow, it's already 1:20. Holy moly. Okay, so we went through this. We can see that this thing is this type. Well, if we're gonna do the simple array, which we wait. Oh, ampersand simple array. Huh. So we went through this, right? All good. Now if we create a pointer to the type simple array object, then we get a constant pointer to an array of 4 elements, which is very similar to the type of the string literal. This demonstrates that the string literal value in Zig is already a pointer to a null-terminated array of bytes. Furthermore, if we take a look at the type of the string object, you will see that it's a slice object, hence the square brackets portion of the type, a sequence of constant U8 values, hence the constant U8 portion of the type. So yeah, so here we have, I guess this is, hey, get me a pointer to simple array, and that returns just a pointer to literally an array of 4 and 32 numbers. Okay, so it's just a pointer. Literally, that's all that was added compared to this. Well, this here is our slice because we forced it to be a slice. Okay, makes sense. This is something we're going to learn more about in practice. So then we have 184, byte versus Unicode points. It's important to point out that each byte in an array is not necessarily a single character. This fact arises from the difference between a single byte and a single Unicode point. Okay? Each byte in an array is not necessarily a single character. Okay? Okay, because Unicode, can have multiple characters, right? The encoding UTF-8 works by assigning a number, which is called a Unicode point, to each character in the string. For example, the character H is stored in UTF-8 as the decimal number 72. This means that the number 72 is the Unicode point for the character H. Each possible character that can appear in UTF-8 encoded string have its own Unicode point. For example, the Latin capital letter A with the stroke, which is this thing, is represented by the number of Unicode point 570. However, this decimal number, 570, is higher than the maximum number stored inside a single byte, which is 255. In other words, the maximum decimal number that can be represented with a single byte is 255. That is why the Unicode point 570 is actually stored inside the computer's memory as bytes C8BA. Okay? So we can see it by going, hey, this, we provided the value, right? So we encoded it already. And then we try to write it, bytes that represent the string object. And we just, okay, print out each byte. Bam. There we go. And we have C8BA. This means that to store the character, capital A with a stroke, in an UTF-8, I mean, it looks like A that is strapped with a seatbelt. In an UTF-8 encoded string, we need to use 2 bytes together to represent the number 570. That is why the relationship between bytes and the Unicode points is not always one-to-one. Each Unicode point is a single character in a string, but not always a single byte corresponds to a single Unicode point. Exactly. All of this means that if you loop through the elements of a string in Zig, you will be looping through the bytes that represent that string, and not through the characters of that string. The A example above, the for loop and needed 2 iterations instead of a single iteration to print the 2 bytes that represent the A with a stroke letter. Now, all English letters, or ASCII letters, if you prefer, can be represented by a single byte. As a consequence, if your UTF-8 string contains only English letters or ASCII letters, then you're lucky, because the number of bytes will be equal to the number of characters in that string. In other words, in this specific situation, the relationship between bytes and Unicode points is 1-to-1. But on the other side, if your string contains other types of letters, for example, you might be working with text data that contains Chinese, Japanese, or Latin letters, then the number of bytes necessary to represent your UTF-8 string will likely be much higher than the number of characters in that string. Alrighty. Oof, that's a lot of words. CPN says, reading writing to any random stack memory itself won't cause segmentation fault? No, it won't. It just doesn't matter. You can do that as long as you actually aim at the correct piece of memory. It's just not healthy for a program. Let's try something. Not this. How can I do pointer arithmetic in Zig? Ugh, that's not how to spell it. So we can have single item pointer. We have number 42. Pointer is pointer to X, right? Then we have an array, and we get the pointer to an array, right? To the first index, and slice preferred for bounce check, and pointer arithmetic operations. So we can say that we have the pointer. Pointer plus 2 is literally pointer plus 2. So it will be plus 2 bytes, I believe. Or no, plus 2 memory points or something like that. Then we have subtraction and indexing. Third element. Blah, blah, blah. Pointer conversion and slicing, memory layout operations. Yeah, you can do all this crazy stuff. Save alternatives, of course. So yeah, in theory, we could do probably something like this. Let's ignore all this stuff. We're gonna say bar number is, let's say this is I32. Why not? Something standard. I32, and that's gonna be 420. All right. And we can actually make it constant. So what if we're gonna say that we have a var pointer to number, and that's gonna be a pointer of a number? I don't think it's gonna be happy because that will be constant pointer. Unused local variable, pointer to a constant value, right? That's probably gonna be unhappy. So now we can say var other pointer is pointer to number plus 2. Can I do that? What is the type here? I want it to be pointer to I32. Unused local variable is never mutated. We can make it constant, right? Because we don't want to make this one. And this one is unused local, but it's not constant anymore. And then we can say, you know what? Other pointer is pointer minus 2. So we went back. And can we say, how do you save the value through a pointer? Because I want to override a constant variable. Pointer plus, pointer minus, third element is pointer this. Let's say I have this. how do I write a new value to what the other pointer is pointing at? CPN says you have to set the const. Yeah, we'll get there. Int reference the pointer to write to the memory. So it's other pointer dot star. Oh, that's a different syntax. So let's do this. We have our number, right? Constant number. We're gonna say standard dot debug print, and we're gonna say number is gonna be this, and this will be a digit, right? So we're gonna say this is dot, this weird syntax, and it's gonna be number. Okay, bam. And then we're gonna copy it, but before we print it, we're gonna say other pointer dot star is 69, right? And we print the number, which is a constant again. Let's see what happens. Will Zig protect us? Incompatible types, constant I32 and comp time. Oh, of course. It was what? CPN, you showed it was. Let's do constant new value is, which is I32 is 69, right? And we can just do this to go around me not knowing how to deal with types yet. Couple of types, const I32 and comp time int. Oh, because we're doing this thing. Really? Hmm. So ChatGPT lies to us? Unless I'm missing something. So we have pointer, which is star I32. Oh, because they specified a pointer to array. No, this fails, dude. This fails. And here go error. This is error. I need to use chat because I don't know at this point. And CPN is already saying pointer plus int cast 2 or pointer cast. Let's try pointer cast first before we ask chat. So it will be ptr cast. And that must have a known result type. Use as to provide explicit result type. Oh, endcast? Same thing. Converts an integer to another integer while keeping the same numerical value. Oh, so we would need to do some as stuff. As, and I don't know, comp time type will be I32 or a pointer to I32. And this will be PTR cast. What the hell am I doing? This is not pretty. Which will we complain now about? Now it complains about this whole thing again. Yep. Let's see what chat says. Because it was error incompatible types, blah. Pointer from int, huh? So I paste that here, let it think. And let's do pointer from, whoa, ptr from int. And this will complain about, I guess I know because it's comp time, as 32, whatever, I32, right? Can I do this or something of the sort? 1, 2, 3, 1, 2, 3. Nope. What if I make it const offset, which will be I32, which is 2. Can I just do offset? And the same thing here, offset. Run. No, type I32 here. Well, should be, yeah. Magically we just add star and it works? No. What does chat say? Try as I32. Oh dear god. Why is it so hard to do math? Let's just see what this says. The error occurs because you have several issues in your code. Number is const. You can't modify it through a pointer. I want to try anyway. Pointer arithmetic on single item pointer is const I32, not this. Type mismatch. You're trying to assign this to that. Oh, here's the corrected version. So it just straight up won't let us. It needs to be var. But I want to break the rules. Let's try to force it with the as stuff. So let's do as I32 add pointer from int to, doesn't show an initial errors, but lots are during runtime. Expected type this, found comp time int, and this is pointed to line 12. Go away. Requires align addresses. Align addresses, what does it mean? It needs to be multiple of 64? Or 32 or something? Aye. Const cast. I don't know what to do with const cast. Comcast? Const cast. Remove const qualifier from a pointer. There we go. I like that idea. Other pointer is const cast of pointer number. There we go. That's the first thing. And what's going to happen now? It won't care anyway. But doesn't mean that we can just skip this whole thing and this whole thing and just say other pointer is this. Will that work? Like magically? Other pointer. Local variable is never mutated. Sure. Oh. Nope, it didn't. Something tells me I'm trying to do something that's not supposed to be able, but if I'm gonna make a variable, this will probably complain that it's not a... Oh, now it changed it. Okay. So now it worked. So something tells me that there's some extra mechanism that just kind of does some magic there. But I hope that by using the pointer arithmetic, I would be able to add something, remove, or do something else. It's just looks like pointer number. If you really want to do pointer arithmetic, though it's not meaningful for a single variable, you need to work with arrays. Oh, really? Array for meaningful arithmetic. Ah, so basically, many item pointer points to number 2, back to number 0. So I can't point to arbitrary number anywhere. Although I think I could. So what if malicious code? Wow, this is a good exercise. What if you know, we have pointed this to this thing, kind of. But what we're gonna do is we're gonna create a constant whatever. Let's do var array, okay? And that will be just an array of I32. That's gonna be 1, 2, 3. Okay? We just have that array. Now, what we want to do is say, hey, I want the pointer to it or something, right? The CPN is like, Zig is safe. But as a programmer, I want the power. If I want it to be not safe, it shouldn't be safe at that point. I'm intending it to be not safe. Okay, standard debug print, blah, blah. Many pointer. So it's pointer to number 0. So that's what we can do, right? We can point to the element number 0. So we can go straight up like this. This would be our array element 0. And this is just some kind of pointer. Then our other pointer looks like it's a normal pointer that points to many pointer plus 2. Sure. So let's just try that first. So pointer will be to many pointer plus 2. And it shows that this is the type. So, okay, we've got something going. And then whatever other pointer is many pointers. So back to number 0, whatever. Doesn't matter. I should be able to say, hey, do the same thing, just do -2. So we go back, but it'll be pointer to number. Oh, whoops. Can we decrease it here? Possibly. And then if we want to change that first number, because we're still pointing at the first number, right? So we should be able to do pointer to number. Let's just verify here. Yeah, we just set a number. Pointer to number is our new value here. Oh, wait, we need to do dot star, and there we go. So in theory, oh, and this needs to be var, of course. Why aren't we declaring it? What the hell? Just many pointer can be const, right? Hopefully. Okay. So we redefine, we change the value, and therefore we don't need any of that. We should be able to print array with a changed value, right? I know that I haven't changed the number itself yet, but I want to see if I can first do this stuff with the array. Expected type of this found this. Many pointer is this. So I don't specify that part and do that part. Why is this as a const? This is not a const. This is so confusing. Comptime end, we have the same kinds of errors. So whatever chat is suggesting doesn't work. So chat doesn't know enough about Zig. SCPN says, oh, you have to remove the 0. You think so? But we don't want to point at that. Index syntax required for unknown length pointer type. Unknown length pointer type. So we went all the way to 16. Index syntax. Oh, because this points to an array. So I need to do... How do I do index syntax? 0? That doesn't make any sense. Like this? I'm guessing. Cannot reference a non-pointer type. I have no idea what I'm doing. But this didn't work. I'm very confused what the hell is going on. Don't know. This just said this is that, right? And that's it. Move the dot star. But the pointer to number is still a pointer. We can just do that? That would be so weird. Oh, we can. That is so weird. What the hell? But that means that we're assigning it just to an element. So what's the pointer of the whole pointer arithmetic? Can I do -3 and just break it? Yes, I can. Okay, so I assigned something somewhere else. And because this is I32, it should go one backwards into this thing in a stack, hopefully. Because this was defined, and then right away we can actually make sure that we define this right away. So let's print our number afterwards. Nope, number didn't change. Oh well, because it still seems like I'm referencing something else. Yeah, this is sketchy. I'll give up for now. We need to learn more about pointers and how things work in the whatever. Print out the addresses. So let's do print, and this will be the many pointer. I don't know how to print the address. I presume it will be many pointer. Let's see if that works. Error, cannot format without specifier S or star as a pointer? So we got I32 at this address. Okay, great. I just need to start adding new lines everywhere because this is getting a little bit out of hand. Okay, now pointer is this. So then we can just copy paste this thing and say that pointer to number is this thing. And then I guess we could do this. Pointer to number is this. Then we're gonna say our pointer to number is +2 after we add it, right? Then after we removed, and I mean, then we just say the value, but something tells me this will be pointless. It all points to, no, the address changes a little bit here and there. Okay, we added 8. Here we removed 8 and removed 2. What? Adding 2 increased from 50 to 58. Going back and removing another 2. Is it always the same? Add 8. Here remove entire 10. Okay, so it removes entire 10. This doesn't add up in my opinion. No, wait, what am I doing? We have 50. 50 plus 2 is 58. And then 58 minus 4 is 48. So this is 2 less than this. This is 2 less than that. So if I'm going to do -8, what the hell is going to happen? $38. So let's just skip this part and just straight up -1. What the hell is going to happen here? If we're gonna do -1, removed by 4, 2, again, 3, again, and lastly we have 4. Okay, so it just increases something, but it doesn't make any sense. 32, and we did something. So CPN says under the hood, it's -2 times size of one element. Yeah, that's what I would expect. But here, size, I guess, would be 4, right? So that kind of makes sense. But again, we can't change this thing. If we're gonna make it var, and at the end of the thing, we're gonna say this is number. And this is pointless discard of local variable. Of course it's pointless. Number is 1 to 3, okay? And it's equally pointless, but now I do this, I just do -1. Oh, now it changed. Okay, so somehow marking as a constant magically protects it. There's some extra mechanism that will protect it. Very interesting. I really wonder how it works. What if we're gonna run it now? And oh, in production, it just doesn't work anymore. Okay. How convenient. In production, it's just gonna not work. I mean, in a release. There are some edge cases we are unaware of. We're pointing at complex system with a stick. Yeah. Yep, don't know how it works. I feel like I shouldn't poke anymore. I'm just wasting my time. And probably everyone else's. Alrighty, so we learned a little bit about UTF-8. If your string contains other types of letters, yeah, if you need to iterate through the characters of a string instead of bytes, then you can use the standard Unicode UTF-8 view struct to create an iterator that iterates through the Unicode points of your string. CPN says, I never dared to venture into the territory. I'm not allowed to. Yeah, I just want to break things instantly. I don't know, it just gives me satisfaction. I don't do that in a day-to-day coding, but on live stream, somehow I'm just compelled to do that. An example below, we loop through the Japanese characters. Each of the 4 characters in the string is represented by 3 bytes, but the for loop iterates 4 times. 1 iteration for each character / Unicode point in this string. Okay, so basically the whole idea is that we create Unicode UTF view, initialized from this, and that somehow doesn't require any allocators, so it's on a stack. I like that reassurance, like, oh, I don't see an allocator anywhere. I know it's on a stack, like 100%. Or maybe not, maybe there's some allocator inside that function that cleans itself up or something? Maybe? Don't know if it's possible to do that in Zig unless you... I mean, I would imagine it's possible. I would want things to work. I don't want to be passing an allocator all the way from the root, all the way down through everything I'm doing, because that would be just horrible. So I hope it doesn't work that way. And it just got con point, this and that. So yeah, while iterator next code point slice. There we go. Okay, so I can see that the iterators with a while loop have some kind of interesting approach, because either the while loop is smart enough to recognize that this is some kind of special iterator, which I presume, because, you know, we extract the code point, right? It's not a true false, while loop would want a true or false, so this is interesting. I'm looking forward to learn about iterators. Okay, some useful functions for strings. In this section, I just want to quickly describe some functions from the Zig standard library that are very useful to use when working with strings, most notably standard memory equal, to compare if two strings are equal, okay? Standard mem equal. I guess we're literally comparing entire memory or something like that. Okay, so that's probably not just for strings. That will be interesting for structs, right? I want to compare if this is the same memory. Split scalar to split a string into an array, excuse me, of substrings given a delimiter value. All right. Split sequence to split a string into an array of substrings given a substring delimiter. Starts with to check if string starts with a substring, ends with trim to remove specific values from both starts and the end of string. So this looks like this is all standard mem, as in memory operations. But I guess it's because a string is simply a, array of bytes. So I guess they just went with generic approach, like, oh, let's not call it string. We don't have a string keyword, so we're just gonna do memory thing, I guess. And we have concatenation, then count of the occurrences of a substring, and replace. Yeah, so we're okay, makes sense. All right. Notice that all of the there we go. All of these functions come from the mem module of the Zig standard library. This module contains multiple functions and methods that are useful to work with memory and sequences of bytes in general. There we go. The equal function is used to check if two arrays of data are equal or not. Since strings are just arbitrary arrays of bytes, we can use this function to compare two strings together. This function returns a Boolean value indicating if the two strings are equal or not. The first argument of this function is the data type of the elements of the arrays that are being compared. All right, bam. Constant U8, Pedro, and standard equal of UA type, right? So which kind of array of what we're comparing? The name here, which is a slice. Okay, we compare a slice to a not slice, and it says true. Interesting. So I guess it just iterates over that because it points at some. Yeah. Okay. So both point at some kind of sequence of bytes of both of specific length. So yeah, we can compare them, right? Okay. Something tells me this is really simple from there. Like, there are some. I presume there are some functions from the CPU itself to just do the quick comparison or something. So that we don't have to manually instruct the processor how to do it. Okay, CPN is possible, but standard library doesn't do it. When there's val, while, and if looks for non-null value, not true or false. Okay, so basically non-null value. So I guess we have the, non-null instead of true or false. Okay, all right, I can see that. So the while loop would work that way. All right. And because I guess it can infer the type that it's going over, if that was returning true or false, it would automatically switch to that mode instead. Okay, I see. We'll learn about it in next chapter, looks like. Okay, so we've got the equal, the split scalar, and split sequence functions are useful to split a string into multiple fragments. Okay. The difference between these two methods is that the split scalar uses a single character as a separator, while split sequence uses a sequence of characters, aka a substring, as the separator. Okay, there is a practical example of these functions later in the book. Okay, it makes sense. It starts with, ends with, it just returns true or false, I guess. And they return Boolean, yep. Indicating if the string, or more precisely the array of data begins or ends with the sequence provided. Yep. So again, we need to specify what type of array that is. All right. And then concat function, as the name suggests concatenate two or more strings together. Because the process of concatenating the strings involves allocating enough space to accommodate all the strings together, this concat function receives an allocator object as input. Really? Allocator. Standard memory concat allocator. Bam, bam. So, so it puts it on a heap because of that? Or am I wrong? And they don't show where they get the allocator from. Very interesting. What if I want to concatenate but not use a allocator? I need to do plus everywhere and do it many times or something? I mean, you can calculate, we have each length, we calculate the sum and just allocate it and return it, and that's it. If I'm not dealing with something long, why do I want to do that? I don't know. As you can imagine, the replace function is used to replace substrings in a string by another substring. Okay, works very similar to replace method from Python. Therefore, you provide a substring to each and every time that the replace function finds a substring within the input string. Okay, so replace from the string 1, L replace with 34 and buffer from here to here. Okay, so which segment of it, right? So in the example below, we are taking the input string hello and replacing all occurrences of substring EL inside this input with 3 and 4 and saving the result inside of the buffer object. As a result, the replace function returns an usize value that indicates how many replacements were performed. Okay. So how to create a buffer? We need to create it manually. Okay, it's undefined because we don't care what it's set to because we're going to set it here. All right. So we're expecting this to be that. What if we're replacing something with something longer? Sounds like a messy business. Okay, so nearly lastly, we have safety in Zig. Because let's move on, we'll probably do a lot of string stuff later. So safety in Zig. A general trend in modern low-level programming languages is safety. As our modern world becomes more interconnected with technology and computers, the data produced by all of this technology becomes one of the most important and also one of the most dangerous assets we have. This is probably the main reason why modern low-level programming languages have been giving great attention to safety, especially memory safety, because memory corruption is still the main target for hackers to exploit. The reality is that we don't have an easy solution for this problem. For now, we only have techniques and strategies that mitigate these problems. As Richard Feldman explains in this most recent GoTo conference talk, excuse me, I'm starting to get tired. We haven't figured out yet way to achieve true safety in technology. In other words, we haven't found a way to build software that won't be exploited with 100% certainty. We can greatly reduce the risk of our software being exploited by ensuring memory safety, for example. But this is not enough to achieve true safety territory. Because even if you write your program in a safe language, hackers can still exploit failures in the operating system where your program is running. For example, maybe the system where your code is running has a backdoor exploit that can still affect your code in unexpected ways. Or also, they can exploit the features from the architecture of your computer. A recently found exploit that involves memory invalidation through a feature of memory tags present in ARM chips is an example of that. Yep. So the question is, what have Zig and other languages been doing to mitigate this problem? If we take Rust as an example, Rust is, for the most part, a memory-safe language by enforcing specific rules to the developer. In other words, the key feature of Rust is the borrow. In other words, the key feature of Rust is the borrow checker. I just don't enjoy dealing with a borrow checker. Basics are fine, but later it just becomes horrible. Forces you to follow a specific logic when you are writing your Rust code. And the Rust compiler will always complain every time you try to go out of this pattern. In contrast, the Zig language is not memory-safe language by default. There are some memory safety features that you get for free in Zig, especially in arrays and pointer objects, but there are other tools offered by the language that are not used by default. In other words, the Zig compiler does not obligate you to use such tools. The tools listed below are related to memory safety. That is, they help you to achieve memory safety in your Zig code. So defer allows you to keep free operations physically close to allocations. This helps you avoid memory leaks, use after free, and also double free problems. Furthermore, it also keeps free operations logically tied to the end of the current scope, which greatly reduces the mental overhead about object lifetime. Yeah, because the moment your code branches into several things, returns early here, maybe runs to the end here, returns early somewhere else, it's easy to just keep, lose track of, did I free everything here? And you spend either extra time checking or you find out a little bit too late. Okay. Error defer helps you to guarantee that your program frees the allocated memory even if a runtime error occurs. Pointers and objects are non-nullable by default. This helps you avoid memory problems that might arise from dereferencing null pointers. Zig offers some native types of allocators called testing allocators that can detect memory leaks and double freeze. These types of allocators are widely used on unit tests, so they transform your unit tests into a weapon that you can use to detect memory problems in your code. Okay, so sounds like we can basically, depending on which kind of runtime we're running on, we can change which allocators we use here and there, and it's, sounds like it's a common interface. Therefore, we can, for tests, run it with something else that, does more checks or whatnot. So yeah, that's fun. I like that. It would be interesting to have like allocators that inject errors or something. That would be super cool. Arrays and slices in Zig have their lengths embedded into the object itself, which makes the Zig compiler very effective in detecting index out of range type of errors and avoiding buffer overflows. Despite these features that Zig offers that are related to memory safety issues, the language also has some rules that help you achieve another type of safety, which is more related to program logic safety. These rules are: pointers and objects are non-nullable by default. Great. Which eliminates an edge case that might break the logic of your program. Switch statements must exhaust all possible options. Awesome. And the Zig compiler forces you to handle every possible error in your program, which is super duper awesome. And lastly, we have the last paragraph, right? Other parts of Zig. We already learned a lot about Zig's syntax and also some pretty technical details about it. Just as a quick recap, we talked about how functions are written in Zig, how to create new objects, new object identifiers, and especially in section 104, how strings work in Zig, how to use arrays and slices, and how to import functionality from other Zig modules. So yeah, this is actually really nice. I really enjoyed that introduction because we had like basics. We didn't focus on how to do loops. We didn't focus how to do all the if-elses, but we have the good basis of, okay, exactly what strings are, because strings, I believe, are often source of confusion. Then dealing with arrays, something that you'll be dealing with a lot. And then, yeah, just, the basics of creation, basic rules of constant var, how it deals with that. Maybe a little bit of functions, like a little bit here and there, but we have like a good cohesive idea of how to do it. But for now, this amount of knowledge is enough for us to continue with this book. Later, over the next chapters, we will talk more about other parts of Zig's syntax that are equally important, such as how object-oriented programming can be done in Zig through struct declarations. Cool. Basic control flow syntax. Enums. Wow, section 7.6. Holy moly. Pointers and optionals in chapter 6. Error handling with try and catch. All the way in chapter 10. Unit tests in chapter 8. Vectors in chapter 17. And build system in chapter 9. Holy moly, it is a lot of chapters, to be honest. But looking at it here on the right, the slider, this is a long article. Is the next article as long? Yep. Oh dear. And yeah, how that works. And we have a bunch of sources that were mentioned throughout the stuff. So control flow will be long. Oh wow. Memory allocators will be nearly as long. Project 1 will be holy moly long. Debugging Zig, not long. Pointers, long-ish. Project 2, very long. Unit tests, long-ish. Build system, long. Error handling, long. Data structure, super long. Project, not that bad. Holy moly, there is a lot of content here. And introducing vector and SIMD is not that long. Huh. Okay. And references. Okay, I'm looking forward to it. Right now, here it's 2:08 in the morning. So, or at night, as I would prefer to say. So yeah, I'll be finishing for tonight because, in 7 hours, less than 7 hours, we have a React stream that I need to get up for, and I need some sleep. My throat needs a break. So thank you so much for hanging out with me. I hope you learned something just like I did. I mean, I learned a ton, and I'm starting to enjoy Zig, so that's fun. I'll see how I like. I mean, so far I like how I'm actually learning some low-level concepts already, which is way earlier than I expected. So I actually might learn Zig, learn Python, and that will fuse into learning Nim finally completely. So, and CPN says I learned some too. Awesome. Probably mostly due to my weird ability to find edge cases. So sorry about that and my tangents. All right. Thank you so much. Everyone have a great day or night or whatever time it is when you're watching this. See you next time. And thank you for hanging out, Travis. It was awesome having some explanations from you. See ya.